Have you ever wondered how giant tunnels are constructed? Where the challenges of the underground world are conquered, and where incredible engineering pushes the limit. Today we will delve deep into the world of tunnel construction, showcasing the giant machines used to dig through planet Earth. Join us as we highlight the groundbreaking techniques and innovations that are redefining tunnel engineering. What about the Cross River Rail project in Australia? This $5.4 billion project involves the construction of a 10.2-kilometer rail line, including a 5.9-kilometer twin tunnel under the Brisbane River and the city centre. Construction of the Cross River Rail began in 2019, with the project expected to be completed by the end of 2024. One of the primary challenges of this project is the need to construct the tunnels beneath a densely populated urban area. To minimize disruption to the city, tunnel boring machines are used to excavate the tunnels. These machines can efficiently and safely bore through the ground while minimizing surface disruption. The project also includes the construction of 4 new underground stations, which are designed to accommodate high-capacity trains and provide modern, accessible facilities for passengers. The project also involves significant upgrades to existing infrastructure, including track realignment and station enhancements. These upgrades are designed to improve the overall capacity and efficiency of Brisbane's rail network, providing a more reliable and convenient service for passengers. Environmental and social considerations are a key focus of the Cross River Rail project. Measures are being implemented to minimize the environmental impact of the construction and operation of the rail line. By providing a reliable and efficient alternative to road transport, the rail line will help reduce traffic congestion and travel times for commuters. In addition to the construction jobs, the operation and maintenance of the rail line will create long-term employment opportunities, further contributing to economic growth and development. Singapore's Deep Tunnel Sewerage System is an ambitious underground wastewater management project designed to meet the country's water needs through the 21st century. Completed in 2008, Phase 1 of the project is a key component of Singapore's approach to sustainable water use, demonstrating foresight in urban planning and engineering. Spanning a length of 48 kilometers, the main tunnel of the system is situated up to 50 meters below the surface. This depth is considerably greater than many urban sewer systems, such as those in older parts of Paris or London, which are typically less than 30 meters deep. The tunnel's diameter is also impressive, stretching up to 6 meters across, capable of handling an immense 2.2 million cubic meters of wastewater daily, which is equivalent to 900 Olympic-sized swimming pools. The construction of Singapore's project was a technical challenge, involving the use of slurry shield tunnel boring machines to navigate through the varied geology of Singapore, from hard granite to soft marine clay. The project cost was approximately $2.7 billion, reflecting both its scale and complexity. A distinctive feature of the project is its integration with a comprehensive water recycling plan, where treated water is reclaimed and then purified further through advanced membrane technologies to produce NEWater, Singapore's brand of high-grade reclaimed water. However, the project was not without its difficulties. During construction, there were challenges related to the variable underground conditions, which required adaptive strategies to prevent disruptions. Additionally, the deep tunnel construction near urban areas posed risks of ground settlement, demanding constant monitoring and precise adjustment of tunneling operations. With plans for Phase 2 underway, which will extend the tunnel by another 100 kilometers, the system will continue to be a cornerstone of Singapore's water management infrastructure. Norway's Coastal Highway project is an unparalleled infrastructure endeavor aimed at revolutionizing travel along the country's rugged western coast. With an estimated cost of $40 billion, this ambitious project seeks to eliminate the need for 7 ferry crossings by connecting the cities of Kristiansand in the south to Trondheim in the north through a continuous, ferry-free highway. Spanning over 1,100 kilometers, it involves the construction of bridges, tunnels, and causeways designed to navigate the challenging Norwegian underwater terrain and weather conditions. A highlight of the project is the proposed construction of the world's longest and deepest submerged floating tunnel, a feat of engineering that exemplifies Norway's innovative approach to overcoming geographical obstacles. This tunnel alone, part of the route across the Sognefjord, is expected to stretch 3.7 kilometers in length and reach depths of up to 392 meters below sea level. Scheduled for completion in 2050, the Coastal Highway project not only aims to significantly reduce travel time across the western coast, but also to boost economic growth and connectivity in remote regions. Let's take a look at the South-North Water Transfer Project. Launched in response to the acute water shortages faced by the northern provinces, including the densely populated and economically pivotal Beijing-Tianjin-Hebei region. This mega project aims to divert water from the Yangtze River in the south to the parched north through a series of canals, tunnels, and advanced pumping stations. Spanning over decades, with its inception dating back to planning stages in the late 20th century, the project is segmented into three distinct routes: the Eastern Route, the Central Route, and the yet-to-be-completed Western Route. Together, they have already transferred billions of cubic meters of water to the northern regions, substantially alleviating water stress in urban and agricultural areas. The financial scale of the South-North Water Transfer Project is staggering, with estimates of the total investment surpassing $80 billion. This figure underscores the complexity and the extensive scope of the project, which involves not only the construction of the physical infrastructure to facilitate the water transfer, but also significant environmental management measures to mitigate the impact on the ecosystems of both the source and recipient areas. The project features state-of-the-art tunneling techniques for crossing under major rivers and traversing diverse terrains, including mountains and urban areas. For example, the project utilizes some of the longest water conveyance tunnels in the world, with advanced boring machines to ensure minimal disruption to the surface. Additionally, it incorporates large-scale pumping stations equipped with high-capacity pumps to lift water across significant elevations along the routes. Furthermore, the project's design incorporates extensive measures for water purification and quality control, ensuring that the transferred water meets the stringent standards required for drinking and irrigation. However, the South-North Water Transfer Project is not without its challenges. The construction of the project's routes and reservoirs has necessitated the relocation of hundreds of thousands of people from their ancestral homes to make way for the infrastructure. This mass relocation has raised issues related to the resettlement process, including adequate compensation, preservation of cultural heritage, and the provision of new livelihood opportunities for those affected. It's time to visit the United Kingdom, where a tunnel is being constructed for an ambitious purpose. The Thames Tideway Tunnel aims to tackle London's over-a-century-old sewage system problem. Officially initiated in 2016, with an estimated completion by 2025. This massive undertaking is designed to prevent millions of tons of untreated sewage from entering the Thames River each year. Stretching over 25 kilometers and delving up to 65 meters below the river, the tunnel is a critical component of modernizing London's sewage disposal and treatment capabilities. Costing approximately £4.9 billion, the project is not just an engineering marvel but also a significant environmental initiative. By intercepting overflow from existing Victorian sewers, the tunnel will ensure that the Thames remains cleaner and more vibrant for future generations. Despite its environmental benefits, the Thames Tideway Tunnel has faced controversy, particularly regarding its financial impact on residents through increased water bills. This crucial development aims to enhance the capacity and efficiency of Melbourne's rail network, addressing the critical need for an urban transit solution to accommodate the city's growing population. Stretching 9 kilometers in length, the Metro Tunnel features twin tunnels, each approximately 7 meters in diameter. The construction involves the use of over 600,000 cubic meters of concrete, enough to fill 240 Olympic-sized swimming pools, and reinforcing it with 70,000 tons of steel. With a total cost estimated at $7 billion, the Melbourne Metro Tunnel is one of the most significant public transport investments in Victorian history. One of the most innovative aspects of the Metro Tunnel is its 5 new underground stations, which are strategically located to maximize accessibility and integrate seamlessly with Melbourne's existing transportation grid. The project includes comprehensive measures to minimize its carbon footprint, such as energy-efficient systems and the use of recycled materials wherever possible. The tunnel's construction utilizes advanced slurry shield tunneling machines that reduce the surface disruption typically associated with subway construction. Moreover, the metro tunnel will increase the network's service capacity by 45%. Facilitating smoother and faster travel across the city and reducing congestion in the CBD by up to 15%. This enhancement is akin to adding an extra freeway into the city, but without the accompanying environmental toll of increased vehicle emissions. This mammoth undertaking, part of the larger Clean Rivers project in Washington, D.C., aims to significantly reduce combined sewer overflows into the Anacostia River, enhancing the river's water quality and complying with federal clean water regulations. The project, which began in 2018, is a critical component in a series of infrastructure improvements designed to modernize the capital's century-old sewer system. Spanning 5 miles in length and located up to 160 feet below ground, the tunnel stretches from the Robert F. Kennedy Stadium to the Rhode Island Avenue NW, with a hefty price tag of approximately $580 million. The construction of the NEBT poses formidable challenges, primarily due to the complexity of drilling a massive tunnel underneath a densely populated urban area. The project utilizes a tunnel boring machine named Chris, a 26-feet diameter behemoth that methodically carves through earth and clay beneath the city. A significant issue the tunnel addresses is the problematic sewer overflow during heavy rainstorms, which historically has led to the pollution of local waterways. The tunnel will capture and store this overflow, transporting it to a treatment facility, thus greatly mitigating the environmental impact and improving the health of the Anacostia River. Throughout the project, DC Water has kept residents informed and involved, addressing concerns ranging from construction noise to local traffic disruptions. Advanced monitoring systems are in place to detect even slight movements of the ground, ensuring that the construction does not affect the integrity of buildings overhead. It's time to investigate an immense underground project in South Korea. Yulhyeon Tunnel, which is the deepest and longest double-track subway tunnel in the world, was completed in 2020 after extensive construction that began in 2011. The tunnel stretches a remarkable 50.3 kilometers, connecting the city of Yuewang with the town of Yulhyeon, and runs as deep as 50 meters underground at some points. The construction of the Yulhyeon Tunnel was a significant undertaking, costing approximately $1.2 billion. The tunnel's role in South Korea's transit infrastructure is pivotal. It facilitates the operation of trains traveling at speeds up to 110 kilometers per hour, which is expected to slash journey times between key South Korean cities by more than an hour. The tunnel's design and construction employed advanced tunnel boring machines and new Austrian tunneling methods, which are considered state-of-the-art in the field of tunnel construction. However, the construction of the Yulhyeon Tunnel was not without its challenges. The project faced significant engineering hurdles, including managing the immense water inflow and stabilizing the tunnel walls in sections with loose earth. In addition to technical challenges, the project also encountered regulatory hurdles. There were concerns about potential impacts on local ecosystems and water tables, which led to rigorous environmental assessments and the implementation of several mitigation measures to protect the surrounding environment. Let's journey to Norway to explore the remarkable Follow Line project. This megaproject is an essential part of the Intercity Triangle, which aims to improve transportation efficiency across the eastern part of Norway. The project began construction in 2015 and opened up to the public in 2022. This new railway line stretches over 22 kilometers and includes the longest railway tunnel in Scandinavia, measuring 19 kilometers. The entire project comes with a hefty price tag of around $2.4 billion, reflecting its vast scale and the cutting-edge technology employed. One of the most ambitious aspects of the Follow Line is its twin tunnel system. Bored through solid rock, these parallel tunnels will drastically reduce travel time between Oslo and Ski, cutting it down to just 11 minutes from the previous 22. The construction of these tunnels involved the use of 4 state-of-the-art tunnel boring machines, each named after historical Norwegian women. These colossal machines, each over 150 meters long, worked simultaneously to excavate the tunnels. A notable engineering challenge of the Follow Line project was the need to navigate through complex geological conditions, including hard gneiss rock and sections of softer ground. Advanced ground freezing techniques were employed in some areas to stabilize the ground, ensuring the safety and stability of the tunnels during excavation. In addition to the tunnels, the Follow Line includes the construction of new stations and upgrades to existing infrastructure. The new ski station is designed to handle increased passenger volumes and will feature modern amenities, including expanded platforms and improved accessibility. These upgrades are expected to accommodate the projected rise in passenger numbers, making train travel more convenient and attractive. It's time to go to Austria next for the Brenner Base Tunnel. This colossal project, designed to streamline European freight and passenger traffic, is not just a tunnel, but a groundbreaking achievement set to transform Transalpine transport. Upon its expected completion in 2032, it will earn the title of the world's longest railway tunnel, stretching an impressive 64 kilometers, or 40 miles beneath the rugged terrain of the Eastern Alps. The vision behind the Brenner Base Tunnel is to provide a more efficient and environmentally friendly alternative for crossing one of Europe's most significant natural barriers, significantly reducing the travel time between Innsbruck, Austria, and Fortezza, Italy. The cost of this monumental undertaking is projected to be around 8.4 billion euros, a figure that underscores the scale and ambition of this cross-border initiative. With a construction saga that began in earnest in 2006, the project has required the mobilization of some of the most advanced tunneling technologies and machinery. The tunnel comprises two main tubes, running parallel and connected by cross passages every 333 meters, ensuring safety and accessibility. It's time to move over to the Blue Plains Tunnel next. This massive infrastructure project is a critical component of DC Water's Clean Rivers project, aimed at drastically reducing combined sewer overflows into the Anacostia, Potomac Rivers, and Rock Creek. The tunnel, completed in 2015, stretches over 24,300 feet in length and is located up to 160 feet below the city's surface. This tunnel was designed to capture and store sewage and stormwater runoff during heavy rains, redirecting up to 100 million gallons of overflow that would have otherwise spilled into local waterways. The project's total cost was approximately $580 million, making it not only one of the largest environmental projects in the city's history, but also a significant investment in sustainable infrastructure. Constructing such a vast underground structure in an urban environment presented numerous challenges. The project team had to navigate around existing utilities and subway tunnels, requiring precise mapping and innovative tunneling techniques. The tunnel was constructed using a tunnel boring machine named Lady Bird, a massive piece of machinery that excavated the tunnel's path while simultaneously laying reinforced concrete to form the tunnel walls. The scope of the Blue Plains Tunnel can be compared to the length of nearly 80 football fields laid end to end. The concrete used in the project would be enough to pave a two-lane road for several miles. Special features of the Blue Plains Tunnel include its state-of-the-art odor control systems designed to treat air before it is vented to the surface, ensuring that the surrounding neighborhoods are not affected by unpleasant smells. Additionally, the project included the construction of diversion facilities, drop shafts, and dewatering pumps, all equipped with cutting-edge technology to handle the massive flow of stormwater and sewage. Environmental impact was carefully managed throughout the construction, with efforts to minimize disruption to the local community and protect the Chesapeake Bay watershed. The project's completion has led to a significant improvement in local water quality and has been a key step toward meeting federal clean water regulations. It's time to travel to Germany, where the Rastatt Tunnel is located. This underground endeavor aims to improve the European rail network, specifically designed to alleviate the strain on existing rail routes and significantly enhance cargo and passenger travel efficiency between Karlsruhe and Basel. The Rastatt Tunnel stretches over a length of 4,270 meters, and it will end up costing around $1.2 billion. Construction kicked off in 2016, but it hasn't been without its challenges. In 2017, a significant setback occurred when part of the tunnel collapsed, causing extensive delays and requiring a reevaluation of project strategies and safety measures. Approximately 2,000 workers have been involved in this mega project, utilizing state-of-the-art construction methods such as tunnel boring machines that carve through the earth with precision. The tunnel features twin tubes, each 10 meters in diameter, which is about as wide as 3 cars parked side by side. These massive tubes are designed to handle the increased rail traffic, with an expected completion and operational date set for 2026. Material-wise, the project is a showcase of modern engineering, using thousands of tons of steel and concrete to ensure structural integrity and safety. In terms of problem solving, the tunnel is a crucial component in the larger strategy to create a more cohesive and efficient European transit network. We have to talk about the Second Avenue Subway megaproject next, located in New York City. Officially part of the Metropolitan Transportation Authority network, this new subway line runs along 2nd Avenue on the east side of Manhattan. The project has been in the conceptual and developmental stages since 1920 but saw its first phase completed and opened to the public on January 1, 2017. Phase 1 of the 2nd Avenue subway cost approximately $4.45 billion and included 3 new stations with a new terminal at 96th Street. The construction of the 2nd Avenue subway involved approximately 6,000 workers at various stages, tackling complex urban engineering challenges such as tunneling beneath densely populated areas and avoiding disruptions to the existing utility infrastructures. This necessitated the use of tunnel boring machines, which are sophisticated pieces of equipment that can efficiently cut through New York's bedrock while minimizing vibrations that could damage building foundations above. The 2nd Avenue subway covers a planned total length of 8.5 miles, once all phases are complete. To put the scale of this project into perspective, the total length of the new subway line would be equivalent to more than 146 football fields laid end to end. Each station is built with expansive, column-free platforms and high ceilings to enhance passenger comfort and safety, a notable departure from many of the city's older subway stations. The 2nd Avenue subway has faced numerous challenges, including budget overruns and delays primarily due to the complexities of constructing a new subway line in one of the world's most built-up urban environments. Comparatively, the cost and scope of the 2nd Avenue subway are similar to those of the Crossrail project in London, although the latter is even larger in scale. Where the Lake Mead Intake No. 3 tackles the critical issue of water scarcity. This monumental project, costing an impressive $817 million, was driven by the urgent need to secure a reliable water supply for Las Vegas, a city that depends heavily on the waters of Lake Mead. Initiated in 2008 and completed in 2015, the project involved drilling a 3-mile-long tunnel beneath Lake Mead, one of the largest man-made lakes in the United States. This was no ordinary task. It required the use of a 1,500-ton tunnel boring machine, cutting through the earth at depths reaching 600 feet below the lake's surface. The purpose: to construct a new intake capable of drawing water from the lake's depths, ensuring access to clean water even as lake levels fluctuated perilously low due to prolonged drought conditions. The construction of Intake No. 3 was not just about securing a water source, it was about innovating for the future. Engineers and workers faced the daunting challenge of working in an environment where temperatures soared, and the risk of flooding within the tunnel was a constant threat. It's time to talk about a Malaysian travel megaproject next, called the Klang Valley MRT, a transformative public transport initiative designed to dramatically improve urban mobility in and around Kuala Lumpur. The SBK line, already operational since July 2017, spans 51 kilometers and features 31 stations, seamlessly connecting key urban and suburban areas. The SSP line, extending over 52.2 kilometers with 37 stations, is poised to further enhance the network's coverage upon its completion. As of recently, the SSP line is targeted for full operation by 2024, promising a significant reduction in travel times and congestion in one of Southeast Asia's most dynamic metropolitan areas. With an estimated investment surpassing $7 billion for the first 2 lines alone, the Klang Valley MRT project stands as one of Malaysia's largest infrastructure undertakings. It underscores the nation's commitment to sustainable urban development, aiming to serve over 2 million passengers daily upon the completion of all phases. But what about an impressive underground traffic tunnel located in the United States? The Port of Miami Tunnel Project is designed to streamline traffic flow to Miami's bustling port facilities, while significantly reducing urban congestion on downtown streets. Completed in 2014, this $1 billion project introduced a 4,200 feet long twin-tube tunnel connecting the MacArthur Causeway on Watson Island with the Port of Miami on Dodge Island. With sections reaching depths of up to 120 feet below the Miami harbor, the Port of Miami Tunnel delves deeper than many other urban infrastructure projects, such as the Big Dig in Boston, which averages 65 feet deep. This depth was critical to allow unrestricted movement of cruise ships and cargo freighters, which frequent one of the busiest cruise ports in the world. The tunnel's construction utilized a world-class tunnel boring machine named Harriet, which was specifically designed for the Miami geology. This 42.3 feet diameter machine was one of the largest of its kind deployed in the United States. Financially, the tunnel project was structured through a public-private partnership, the first of its kind in Florida's history. The tunnel is equipped with state-of-the-art safety systems, including 91 CCTV cameras. These comprehensive measures surpass the setups found in smaller tunnels where budget constraints often limit such extensive safety implementations. Despite its successful completion, the Port of Miami Tunnel project encountered numerous challenges. Initial geological surveys underestimated the complexity of the Miami limestone, leading to adjustments in the tunneling work that delayed the project by several months. Moreover, the project's deep excavation close to densely populated urban areas and vulnerable marine environments posed significant logistical and environmental hurdles, necessitating rigorous compliance with stringent regulations. The next project on our list is a tunnel that's connecting two major countries, the Fehmarn Belt Fixed Link. This ambitious project, with an estimated cost of 7.4 billion euros, is not just another infrastructure endeavor. It's a bold leap towards uniting regions and enhancing mobility in Europe by connecting Germany and Denmark. Spanning approximately 18 kilometers, it's poised to become the world's longest immersed tunnel, designed for both rail and road traffic. The construction employs the use of specially designed ships to lay sections of the tunnel on the seabed, a method that underscores the innovative spirit of this undertaking. The tunnel comprises 79 individual segments, each meticulously fabricated off-site, showcasing the meticulous planning and precision that underpin this colossal project. The planned completion date for this project is unknown, but they're aiming to open it somewhere in 2029. Next up, it's time to shift our focus to Italy and delve into the ambitious Terzo Valico dei Giovi project. Located in the northwestern region of Italy, this high-speed rail line is designed to connect the city of Genoa with the broader European network, significantly improving freight and passenger transport across the region. The project began construction in 2013 and is expected to be completed by 2026. This project is part of the broader Trans-European Transport Network, which aims to integrate European rail systems and boost economic growth by improving transportation efficiency. The total investment for this project is estimated at over $7 billion. The new rail line will stretch approximately 33 miles, featuring a series of tunnels that make up over 70% of the route. These tunnels, including the Valico Tunnel, which alone spans 17 miles, are designed to traverse the rugged Apennine Mountains, reducing travel times and creating a more direct route between Genoa and the Po Valley. Constructing these tunnels has presented significant engineering challenges. The project involves boring through complex geological formations, which require advanced drilling techniques and meticulous planning. Tunnel boring machines are being used to ensure precision and safety, cutting through rock while minimizing disruption to the surface above. One of the project's primary goals is to enhance freight transport between the Port of Genoa and northern Italy, as well as other European destinations. The Port of Genoa is one of Italy's busiest, and the Terzo Valico dei Giovi will facilitate the movement of goods by providing a faster and more efficient rail link. In addition to freight, the new rail line will significantly improve passenger travel. Currently, journeys between Genoa and Milan can take over an hour and a half by train. Once the Terzo Valico dei Giovi is operational, this travel time will be reduced to approximately 50 minutes. The East Side Access Project exemplifies the challenges and triumphs of urban tunneling and railway construction. With an estimated cost of over $11 billion, it ranks as one of the most expensive railway projects in the world. This ambitious project aims to connect the Long Island Railroad to a new terminal beneath Grand Central Terminal, offering a direct route that was previously unavailable to thousands of commuters. The East Side Access includes approximately 8 miles of tunneling beneath Manhattan's densely packed urban environment. These tunnels were not merely dug but meticulously carved through some of the most challenging geological conditions, including hard rock and water-bearing sediments. Did you know that the project necessitated the excavation of about 2 million cubic yards of rock? This is equivalent to filling the Empire State Building nearly 2 times. The construction also involves the creation of a new terminal beneath Grand Central, consisting of multiple levels of concourses and platforms. This terminal is being constructed more than 140 feet below street level, requiring innovative solutions for ventilation, lighting, and passenger flow. We have to talk about Beijing's massive underground subway megaproject next. With its first line opening in 1969, the network has expanded to include 25 lines, encompassing over 700 kilometers of track and approximately 428 stations, making it one of the longest metro systems globally. This sheer size surpasses many other major systems, such as New York subway, which measures about 380 kilometers in length. Diving into the depths, the Beijing subway's deepest point is at the Daxing Airport Express line, which reaches 30 meters below the ground. The construction costs for this colossal network have amounted to billions of dollars, with recent expansions like the Line 7 and Line 14 collectively costing over $7.3 billion. One unique aspect of the Beijing subway is its adaptation to the city's geological conditions, which include areas of high seismic activity. The system is designed with earthquake resistance features that allow it to withstand tremors, a critical capability not integrated into many older and less robust subway designs around the world. Moreover, the Beijing system incorporates state-of-the-art technologies such as contactless ticketing, high-speed train sets capable of exceeding speeds of 100 kilometers per hour, and an automated ventilation system that is considered one of the most advanced in the world. Challenges have been persistent throughout its development, including issues with overcrowding, particularly during peak hours where some lines see passenger loads far exceeding their design capacity. To combat this, the government has implemented dynamic pricing models during rush hours and has continuously expanded lines and added new ones to distribute passenger flow more evenly. As the system continues to grow, with plans to exceed 1,000 kilometers by 2030, it remains a critical component of Beijing's urban landscape. We have to talk about the Metro Manila subway project next. In the bustling heart of the Philippines, a transformative project is underway that promises to redefine urban mobility in Southeast Asia's megacities. Spanning an impressive 36 kilometers, the Metro Manila subway is designed to connect the northern city of Valenzuela to the southern end at NEA Terminal 3 in Pasay City, with 15 stations planned along this vital transit artery. Launched in February 2019, with a targeted completion for full operation by 2025. This mega project involves an estimated cost of $7 billion. The subway system is projected to serve up to 370,000 passengers daily in its initial year, with the capacity expected to increase to over 1 million passengers daily in the subsequent years. This monumental increase in public transit capacity is crucial for a city where commuters currently face some of the longest travel times in the world. One of the most significant challenges faced by this project is the engineering required to build deep underground in an area known for its high water table and susceptibility to flooding. Advanced Japanese tunneling technology is being employed, including the use of massive, state-of-the-art shield tunnel boring machines that can cut through the complex subterranean landscape of Metro Manila. The construction of the Metro Manila subway involves around 6,000 workers at its peak, including a blend of local talent and international experts. The workforce is not only constructing the subway but also engaging in massive road and utility diversions, with the movement of utilities alone being a colossal task equivalent to relocating the infrastructure of a small city. Special features of the Metro Manila subway include state-of-the-art ventilation systems, floodgates, and earthquake-resistant design elements that ensure the safety and resilience of the subway. Each station will also feature modern amenities and seamless connections to other forms of transportation, integrating the subway into the broader transport network of the city. Let's take a closer look at the Second Midtown Tunnel project. Located under the Elizabeth River, the Second Midtown Tunnel connects the cities of Norfolk and Portsmouth. Its construction began in 2012 and reached completion in 2016. This project involved building a new two-lane tunnel parallel to the existing Midtown Tunnel, effectively doubling the capacity of this crucial traffic artery. With a cost of $2.1 billion, the construction process for the Second Midtown Tunnel was both innovative and complex. Unlike traditional tunneling methods, this project used an immersed tube technique. Prefabricated tunnel sections, each weighing approximately 16,000 tons, were constructed in a dry dock. These sections were then floated to the site, submerged into a pre-dug trench on the riverbed, and connected to form the tunnel. This method minimized disruption to river traffic and ensured precise alignment of the tunnel sections. The new tunnel not only alleviates traffic congestion but also enhances safety and travel times for thousands of commuters. In terms of environmental considerations, the project included several measures to mitigate its impact. This included careful monitoring of water quality during construction and the use of innovative techniques to manage and minimize sediment displacement. The Second Midtown Tunnel also features modern safety enhancements, such as advanced ventilation systems, state-of-the-art lighting, and emergency response facilities. These upgrades ensure the tunnel meets contemporary standards for infrastructure resilience and commuter safety. Comparing this project to other major infrastructure endeavors, the Second Midtown Tunnel stands out for its strategic importance in regional connectivity and its use of advanced construction techniques. It plays a crucial role in supporting the economic vitality of the Hampton Roads area, facilitating smoother and more efficient transportation for both commercial and personal use. But what about the most expensive megaproject located in Europe? High Speed 2 is poised to be one of the most transformative rail projects in European history, designed to connect London with the north of England and potentially the central belt of Scotland. The project's primary objective is to enhance connectivity, reduce travel times between major cities, and alleviate congestion on the UK's existing rail network. Initiated with the intention to drastically reduce travel times, HS2 will see trains operating at speeds of up to 250 miles per hour. Upon its anticipated completion, the journey from London to Birmingham will be cut to just 45 minutes, compared to the current duration of an hour and 20 minutes. The project will lay down hundreds of miles of track, which requires the excavation and movement of millions of tons of earth. The project's scale is mirrored by its workforce requirements, with tens of thousands of jobs expected to be created during construction. Additionally, HS2 is a catalyst for technology and innovation in construction, employing advanced techniques in tunneling, bridging, and environmental conservation. The trains are planned to be powered by zero-carbon energy from day one of operations, aligning with the UK's broader environmental goals. The new rail lines themselves are designed to integrate with the natural landscape, incorporating green tunnels and wildlife crossings to minimize the environmental impact. However, HS2 has faced considerable problems and controversies, particularly regarding its cost and the environmental impact of its construction. With its budget now revised to an estimated $130 billion, HS2 ranks as the most expensive infrastructure project undertaken in Europe. This investment underscores the UK government's commitment to revolutionizing transport, but has also sparked debates on fiscal responsibility and environmental stewardship. Despite these challenges, the potential benefits of HS2 are substantial. It is expected to double the number of seats available out of London Euston, reducing road congestion. We move over to New York next for the Hudson Tunnel project. This massive project aims to construct a new rail tunnel under the Hudson River, directly addressing the critical need for modernized and reliable rail connections between New Jersey and Manhattan. Currently estimated to cost around $11.6 billion, the Hudson Tunnel project involves constructing a new two-track rail tunnel, refurbishing the existing century-old tunnel, and making related infrastructure improvements. Upon completion in 2026, it is expected to significantly reduce the risk of severe disruptions in daily commutes and national rail transport. The new tunnel's construction is a complex challenge, requiring sophisticated tunnel boring and under-river drilling techniques to navigate the geological and environmental sensitivities of the Hudson River's underwater terrain. The existing North River Tunnel, which currently serves as the only rail link under the Hudson for Amtrak and New Jersey Transit trains, has been in service since 1910 and was severely damaged during Hurricane Sandy in 2012. The construction of the new tunnel will allow this old tunnel to be closed for repairs without disrupting the critical train services it provides. To understand the scale of the Hudson Tunnel project, consider that the new tunnel will extend about 2.5 miles under the riverbed, involving millions of cubic feet of excavated earth, enough to fill over 1,000 Olympic-sized swimming pools. The project's challenges are immense, from navigating bureaucratic hurdles and securing funding agreements across multiple government entities, to the physical difficulties of urban tunneling. Let's travel over to Sao Paulo, one of the largest and most populous cities in Brazil. They are enhancing its public transportation infrastructure with the Sao Paulo Metro Line 6. Often referred to as the Orange Line, this project aims to alleviate the chronic traffic congestion in the metropolitan area. Spanning approximately 15 miles, Line 6 will connect the northwest region of Sao Paulo with the downtown area, providing a crucial link for daily commuters. Construction of the Sao Paulo Metro Line 6 commenced in 2015, but faced several delays due to financial and administrative challenges. However, the project gained momentum in recent years, with a renewed commitment to completing this vital infrastructure. The line will include 15 stations, each designed to accommodate a significant number of passengers with modern facilities and accessibility features. The stations are strategically located to serve densely populated neighborhoods, universities, and commercial areas, enhancing the overall connectivity of the city's metro network. One of the significant engineering feats of this project involves the use of tunnel boring machines to excavate the tunnels. These machines, known for their precision and efficiency, are capable of drilling through various soil types found in Sao Paulo. The machines also help minimize surface disruption, a critical factor in a bustling city. The tunnels are reinforced with precast concrete segments, ensuring their structural integrity and longevity. The expected daily ridership of the Sao Paulo Metro Line 6 is projected to exceed 600,000 passengers, significantly reducing the number of vehicles on the road and thereby decreasing traffic congestion and pollution. The integration of this line with other metro lines and bus networks will provide seamless transit options for millions of residents and visitors. The project's budget is estimated at approximately $3 billion, reflecting its scale and complexity. The successful completion of Line 6 is anticipated to not only improve transportation efficiency, but also boost the local economy by creating jobs. Let's embark on a journey to Norway to uncover the Nordøyvegen project. Spanning over 13 miles, this monumental endeavor weaves together a series of tunnels, bridges, and causeways that traverse some of the most challenging terrain in the region. The project commenced in 2017, driven by the need to enhance connectivity and improve the lives of the island residents. At its heart lies the construction of 5 tunnels, the longest of which stretches for nearly 4 miles beneath the seabed. Complementing these tunnels are several grand bridges, including the iconic Lepsøy Bridge, which arches gracefully over the treacherous waters below. Each bridge is designed not only to withstand the harsh maritime climate, but also to blend seamlessly with the stunning natural surroundings, reflecting a harmonious balance between human achievement. The scale of Nordøyvegen is underscored by its substantial financial commitment, with costs estimated at around $590 million. This investment reflects the project's importance to the region, promising significant economic and social benefits. Once completed, the road will drastically reduce travel times, transforming what was once a multi-hour ferry journey into a seamless drive of mere minutes. Building Nordøyvegen presented formidable challenges. The construction teams had to contend with the relentless forces of nature, including unpredictable weather and the powerful currents of the Norwegian Sea. The project's impact extends far beyond mere connectivity. It is set to revitalize the local economy, providing easier access for businesses and boosting tourism. The improved infrastructure will attract new opportunities and investments, fostering growth and development in these previously isolated communities. The Central Artery Tunnel Project, famously known as the Big Dig in Boston, Massachusetts, stands as one of the most complex urban infrastructure projects ever undertaken in the United States. Originally estimated at $2.8 billion, the project's cost skyrocketed to over $21.9 billion by its completion. Spanning from 1988 until 2006, the Big Dig aimed to address the chronic traffic congestion on Boston's Central Artery by relocating it underground and extending the Massachusetts Turnpike through a new tunnel under Boston Harbor. A key feature of the Big Dig was the construction of the Ted Williams Tunnel, the first major component completed in 1995, which extends I-90 to Logan Airport. Did you know that the project utilized over 3.8 million cubic yards of concrete, enough to lay a sidewalk 3 feet wide from Boston to San Francisco? The Leonard P. Zachem Bunker Hill Memorial Bridge is also part of this project, being the world's widest cable-stayed bridge, celebrated for its aesthetic appeal and structural design. Nestled in the Vermilion Range of Minnesota, this project harbors the state's oldest and deepest iron ore mine, which commenced operations in 1882 and continued until 1962. This site has transitioned from a high-grade ore production facility to a hub for scientific research and public education. The mine's deepest sections extend nearly half a mile underground, setting it apart as one of the most substantial vertical shaft mines in the United States. During its 80 years of operation, the Soudan mine produced over 15.5 million tons of ore, a staggering amount that contributed significantly to the region's economic development. This production level was critical for the United States steel industry, particularly during both world wars. Transforming the site into Soudan Underground Mine State Park involved significant effort, with the state of Minnesota investing heavily to preserve this historical landmark. The transition included extensive renovations to stabilize old mine workings and adapt the underground tunnels for safe public tours and scientific research, specifically in physics. The park now hosts a state-of-the-art physics laboratory, which was established to study particle physics, including investigations into the elusive dark matter. This lab, located in the mine's lower levels, utilizes the Earth's natural shielding against cosmic rays to operate highly sensitive detectors, such as the MINOS experiment, which tracks neutrinos from the Fermilab in Illinois over a distance of 450 miles. United States also has constructed some really impressive underwater megaprojects, such as the Chesapeake Bay Bridge Tunnel, stretching over the waters of the Chesapeake Bay to connect Virginia's eastern shore with the mainland. Opened in 1964 and expanded over the years, this 23-mile marvel is not just a bridge but a series of bridges, tunnels, and artificial islands. Constructed at a cost of approximately $200 million at its inception, with subsequent expansions adding to the investment, the Bay Tunnel stands as a testament to human ingenuity in overcoming geographical challenges. The structure includes 2 one-mile tunnels that dive beneath the bay, allowing ships to pass unimpeded above, while miles of low-lying trestle bridges provide breathtaking views of the surrounding waters. The use of the bridge-tunnel combination was a pioneering approach, providing a direct, uninterrupted flow of traffic across the bay and demonstrating a harmonious blend of functionality. Let's travel to Malaysia next, where a huge railway megaproject is underway, called the East Coast Rail Link. Stretching approximately 665 kilometers, the project will connect the strategic port town of Port Klang on the Straits of Malacca to Kota Baru in the northeast, slashing travel time between the east and west coasts of peninsular Malaysia. Commenced in 2017 with an anticipated completion in 2026, this ambitious project is not just a rail line, it is a key part of China's Belt and Road Initiative, showcasing a significant international collaboration. With a staggering investment estimated at $11 billion, the link is set to be one of the most extensive infrastructure projects ever undertaken in the region. This project is designed to facilitate up to 5.4 million passengers and 53 million tons of cargo annually by 2030, aiming to bolster economic growth by enhancing trade, tourism, and development in the less developed eastern regions. One of the most striking features of the rail link is its engineering challenges. The route traverses rugged terrain, requiring the construction of more than 200 bridges and 14 tunnels through the Titiwangsa mountain range. The longest of these tunnels stretches over 16 kilometers, making it one of the longest rail tunnels in Southeast Asia. The project employs advanced tunneling methods such as tunnel boring machines and new Austrian tunneling methods, which are essential for managing the complex geology of the region. The project also introduces cutting-edge rail technology, including dual-gauge tracks that accommodate both passenger and freight trains, capable of speeds up to 160 kilometers per hour for passengers and 80 for freight. Comparatively, the length of the rail link is equivalent to the distance from London to Zurich, illustrating the vast scale of this project. However, the project has faced its share of controversies and challenges, including environmental concerns and the displacement of local communities. Additionally, financial renegotiations and geopolitical tensions have occasionally stalled progress, reflecting the complex dynamics involved in large-scale international infrastructure projects. Upon completion, the railway will significantly reduce the travel time between the east and west coasts from 12 hours to just 4 hours by train. We have to travel to Chicago for the next mega project. The Chicago Deep Tunnel Project, formerly known as the Tunnel and Reservoir Plan, is an ambitious civil engineering project designed to address the critical issues of urban flooding and water pollution in the city. Spanning over 100 miles of deep, large-diameter tunnels located up to 300 feet beneath the city, the Deep Tunnel Project is one of the largest and most comprehensive urban water projects in the world. With a total estimated cost projected at $3 billion. One of the primary functions of the tunnel is to capture and store stormwater runoff and sewage that would otherwise overflow into the city's rivers and Lake Michigan during heavy rain events. This system can hold up to 2.3 billion gallons of stormwater, significantly reducing the frequency and severity of water pollution incidents and urban flooding in the region. The construction of the Deep Tunnel Project has been a monumental undertaking. It required the use of massive tunnel boring machines, some of the largest in the world, which have carved out tunnels with diameters ranging from 9 to 33 feet. One of the distinguishing features of the project is the construction of 3 immense reservoirs, designed to work in conjunction with the tunnels. The largest of these, the Thornton Composite Reservoir, was completed in 2015 and covers 300 acres, making it one of the largest man-made reservoirs for stormwater management in the world. Its capacity is so vast that it could theoretically hold all the water used to fill over 2,000 Olympic-sized swimming pools. In comparison to other megaprojects, such as the Boston Big Dig or the London Sewer System upgrade, the Chicago Deep Tunnel Project stands out for its scale and its focus on water management in a densely populated urban setting. Let's delve into the Northgate Link Extension, a transformative addition to Seattle's public transportation network. Completed at a cost of $1.9 billion, this project is a cornerstone of the region's efforts to enhance urban mobility and reduce traffic congestion. Breaking ground in 2012 and opening to the public in October 2021, the Northgate Link Extension stretches the city's light rail system by 4.3 miles, connecting the University of Washington to Northgate. This crucial extension includes 3 new stations, strategically located to serve key residential and commercial hubs in northern Seattle. A defining feature of the Northgate Link Extension is the engineering marvel of its twin tunnels, constructed using state-of-the-art tunnel boring machines. These machines, dubbed Brenda and Pamela, excavated deep beneath the city, navigating complex soil conditions and existing underground infrastructure with remarkable precision. The construction process engaged thousands of workers and required intricate planning and coordination. Each new station is designed with a focus on accessibility, safety, and community integration, featuring modern amenities and public art installations that enhance the commuter experience. The Northgate Link Extension significantly reduces travel times, with the journey from Northgate to downtown Seattle now taking just 14 minutes. This improvement is expected to ease road traffic and provide a reliable alternative to driving, fostering greater use of public transportation. The project's impact on Seattle's urban landscape is profound, revitalizing neighborhoods and stimulating economic growth around the new stations. But what about a brand new tunnel that's currently being built? The Túnel del Toyo, currently under construction in Colombia, is set to become the longest road tunnel in Latin America. Spanning approximately 6.2 miles, this ambitious project aims to significantly reduce travel time between Medellin, Colombia's second-largest city, and the key port of Uraba. This reduction in travel time is expected to boost trade and economic activities in the region. Construction of the Túnel del Toyo began in 2015, and the project is expected to be completed by late 2024. The tunnel will cut through the rugged Andean mountains, presenting numerous engineering challenges. The project involves extensive geological surveys and the use of advanced tunneling techniques to navigate the complex terrain safely. The Túnel del Toyo is designed as a dual-bore tunnel, with each bore accommodating 2 lanes of traffic. This design ensures a smooth flow of vehicles and enhances safety. The project also includes the construction of access roads and ventilation systems to maintain air quality within the tunnel. One of the critical benefits of the Túnel del Toyo is the expected reduction in travel time. Currently, the journey between Medellin and Uraba takes about 6 hours by road, traversing winding mountain roads that are often prone to landslides and other hazards. The tunnel will cut this travel time to approximately 3 hours, providing a more direct and safer route. The Túnel del Toyo project is estimated to cost around $1 billion, with funding sourced from both national and regional governments. Environmental considerations are also a key aspect of the project. The construction process includes measures to minimize the impact on local ecosystems, such as the relocation of wildlife and reforestation efforts. The tunnel's design also incorporates advanced drainage systems to manage water flow and prevent flooding. We have to travel over to Austria for our next project. The Koralm Tunnel is one of the most ambitious railway infrastructure projects in Europe. This 20-mile-long tunnel, part of the Koralm Railway, will connect the cities of Graz and Klagenfurt, significantly reducing travel time and enhancing connectivity in the region. The tunnel passes through the Eastern Alps, making its construction a remarkable engineering feat. Construction of the Koralm Tunnel began in 2008. With completion expected by 2026. The project involves a substantial investment, estimated at around $5.4 billion. One of the primary challenges has been tunneling through the complex geological conditions of the Alps, which requires advanced tunneling techniques and machinery. The tunnel will feature twin tubes, each with a diameter of around 30 feet, allowing for separate tracks for trains traveling in opposite directions. The design includes state-of-the-art safety systems, such as emergency exits, ventilation systems, and fire protection measures. These features are essential to ensure the safety and reliability of the tunnel, given its length and the volume of traffic it will handle. The construction of the Koralm Tunnel involves the use of tunnel boring machines, which are capable of excavating through rock and soil with precision. The machines are equipped with cutting-edge technology to manage the challenges posed by the varying geological conditions. The project also includes the construction of access tunnels, ventilation shafts, and support structures to facilitate the excavation and operation of the main tunnels. Once completed, the tunnel will reduce travel time between Graz and Klagenfurt to just 45 minutes, compared to the current 3-hour journey by car. Let's travel over to Australia for the WestConnex project. This $16.8 billion development involves the construction of 33 kilometers of new and upgraded motorways, including tunnels, interchanges, and expressways. One of the significant engineering challenges in the WestConnex project is constructing the extensive tunnel network. The tunnels are built using tunnel boring machines, which can simultaneously excavate and line the tunnels with concrete segments. This method ensures a smooth and efficient construction process, minimizing disruption to the surface environment. The boring machines used in the project are some of the largest in the world, with diameters of up to 15.5 meters. Another innovative aspect of the WestConnex project is using smart technology to manage traffic flow and improve safety. The motorways are equipped with an intelligent transport system that includes real-time traffic monitoring, electronic signage, and automated incident detection. This system helps manage congestion and ensures a swift response to any incidents, enhancing the overall efficiency of the road network. Measures have been taken to minimize the environmental impact of the construction and operation of the motorways. This includes using low-emission construction equipment, implementing noise barriers, and green walls to reduce noise pollution. One of the key benefits of the West Connects project is the significant reduction in travel times for commuters. By providing new and upgraded motorways, the project aims to alleviate congestion on some of Sydney's busiest roads, making it easier and faster for people to travel across the city. Let's move to the next impressive Chinese mega-project, called the Chongqing-Kunming High-Speed Railway. This pivotal project, stretching over 720 kilometers or 447 miles, connects two major cities in southwest China, Chongqing and Kunming. The railway, part of China's grand plan to create a 30,000-kilometer high-speed rail network, underscores the nation's ambition to lead globally in rail technology. Costing approximately 100 billion yuan or $15 billion, the Chongqing-Kunming High-Speed Railway is not just an economic investment, but a technological showcase. The project features numerous tunnels and bridges, including the world-renowned Wulong Mountain Superbridge. The railway reduces the travel time between Chongqing and Kunming from over 20 hours to just 4.5 hours, significantly impacting the social and economic landscape of the region. It enhances accessibility, promotes tourism, and fosters economic integration between the southwestern provinces. The construction of this railway employed cutting-edge machinery and materials, with a focus on durability and safety. High-strength steel, advanced concrete composites, and state-of-the-art track-laying techniques were utilized, ensuring that the railway could withstand the region's seismic activity. The use of tunnel boring machines and bridge-building gantries played a pivotal role in accelerating the construction pace, demonstrating China's prowess in leveraging technology for infrastructure development. One of the key challenges encountered during the construction was the environmental impact, particularly in ecologically sensitive areas. The project team implemented several mitigation strategies, such as rerouting sections of the track, constructing wildlife crossings over and under the railway, and implementing strict construction practices to minimize the disturbance to the natural landscape. But the project has not been without its controversies, including concerns over land acquisition and environmental degradation. The government and project developers have faced criticism over the lack of transparency and adequate compensation for those affected. Despite these challenges, the Chongqing-Kunming High-Speed Railway remains a symbol of progress and a critical component of China's vision for a modern country. Let's check out the Grand Paris Express, France's most ambitious public transport project to date. This colossal undertaking involves the creation of 4 new automatic metro lines and the extension of existing Line 14. By its completion, the network will add approximately 200 kilometers or 124 miles of track and 68 new stations to the Paris Metro, aiming to serve 2 million passengers daily. With an estimated cost of over 35 billion euros, the Grand Paris Express is designed to enhance connectivity across the suburban areas of Paris, directly linking various communes to the city center and major airports without the need for transfers. This project is not just about facilitating easier commutes, it's about stimulating economic growth, reducing traffic congestion, and promoting sustainable urban development. The initial phases of the Grand Paris Express have already begun, with a completion date for the entire network projected by 2030. However, specific lines and stations will open in stages, with the first new routes expected to be operational before the 2024 Paris Olympics. The Wieliczka salt mine in Poland is an astonishing subterranean network that stretches to depths of up to 327 meters, or 1,073 feet below the surface, covering an expansive area of 2.4 million square meters. Operational for over 700 years since its inception in the 13th century, the mine is one of the world's oldest continuously running salt mines, only ceasing commercial salt production in 2007 due to flooding and the low price of salt on the global market. This historic mine features a labyrinth of tunnels, chambers, and galleries that extend over 178 miles, though only a small portion is accessible to the public. By comparison, the equally historic but much shallower Kira Salt Mine in Pakistan extends just 25 miles of passages. One of the mine's most unique attributes is its underground city, which includes chapels, a cathedral, and numerous sculptures all carved from rock salt by the miners. Financially, the development of Wieliczka Salt Mine over the centuries has involved significant investment, particularly in its conversion into a major tourism and health resort. The site now attracts approximately 1.2 million visitors annually, generating substantial revenue that supports its preservation and the local economy. Throughout its long history, Wieliczka has faced numerous challenges, including the threat of mine flooding, which on several occasions risked catastrophic collapses. These were mitigated through modern engineering efforts that included the installation of high-volume pumps and new drainage systems, ensuring the mine's stability and the safety of its visitors. Besides that, the preservation of this UNESCO World Heritage Site involves complex conservation practices. The saline environment, which is beneficial for health, poses a constant threat to the mine's structural integrity, accelerating the deterioration of wooden structures and necessitating continuous maintenance efforts. It's time to move on to one of the biggest pipeline megaprojects in the world, called the Nord Stream gas pipeline. Stretching beneath the Baltic Sea to connect Russia with Germany, this strategic pipeline operation since November 2011 spans approximately 1224 kilometers, making it one of the longest offshore gas pipelines in the world. With a total project cost estimated at 8.8 billion euros, the Nord Stream has capacity to transport up to 55 billion cubic meters of gas annually, playing a crucial role in ensuring energy security and diversification of supply routes in Europe. Constructed using state-of-the-art technology, the pipeline comprises two parallel lines, each made from tens of thousands of steel pipes, welded together on board specialized vessels. These pipes, coated for corrosion resistance, were laid on the seabed by some of the world's most advanced laying ships, navigating through challenging marine conditions. Despite its technical achievements, Nord Stream has been mired in controversy. Critics argue that it increases European dependency on Russian gas, posing geopolitical risks. Environmental groups have also raised concerns about the potential impacts on the Baltic Sea's delicate ecosystem. Yet, proponents highlight its contribution to energy security and lower carbon emissions compared to coal and oil. Let's move over to Mexico next, where the Tren Maya project is set to be completed. The railway project, extending over 1,500 kilometers, will connect 19 stations and is expected to revolutionize transportation in southeastern Mexico. Tren Maya's construction involves laying enough tracks to stretch from Mexico City to Chicago, illustrating the project's vast scale. The train will serve both freight and passenger services, aiming to transport approximately 3 million passengers and a significant amount of goods annually once fully operational. The design includes a dual-track system for most of its route, allowing trains to travel at speeds up to 160 kilometers per hour, which will cut travel time between key cities by more than half compared to current road travel times. The project's budget, estimated at $15 billion, positions Tren Maya as one of the largest public works projects in Mexican history. Environmental considerations are integral to the project's design. The route is planned to minimize ecological impact, using existing transit corridors wherever possible to avoid deforestation in sensitive areas like the Mayan jungle. The trains are also expected to be powered by biodiesel, reducing carbon emissions compared to traditional diesel engines. Tren Maya is forecasted to dramatically increase tourism revenues by providing easier access to remote archaeological sites that are currently difficult to reach. This accessibility is anticipated to bring an additional 1 million tourists annually, potentially increasing tourism revenues by over $400 million per year. The construction phase alone has created approximately 100,000 jobs, and the operational phase is expected to support many more. Tren Maya's construction process utilizes advanced geological and hydrological engineering to protect the region's numerous cenotes and underground water reserves. Techniques include elevated tracks and special tunneling methods to prevent contamination or structural damage to these crucial environmental features. Let's travel over to the next mega project, the Los Angeles County Metro Purple Line Extension, which is a massive $9.3 billion rail project that's stretching the definition of urban transit development. Extending the Metro Purple Line by 9 miles, this project is not just about adding tracks, it's about seamlessly connecting key sectors of the city, from the skyscrapers of downtown La to the vaunted gates of the University of California. Slated for completion in 2027, the Purple Line extension is currently a hive of activity with over 5,000 workers bustling daily. Building a subway in an area prone to earthquakes demands cutting-edge construction techniques. The team employs advanced tunneling methods, including earth pressure balance machines that delicately burrow beneath the city, ensuring minimal disruption to the surface life and structural integrity of the buildings above. This project solves critical transportation problems in one of America's most congested cities by offering a reliable, high-speed alternative to road travel, effectively reducing traffic and the city's carbon footprint. Once operational, it's expected to serve about 49,000 riders daily. Comparing this to the scale of other megaprojects around the globe, the Purple Line extension's budget overshadows the construction costs of the new Wembley Stadium in London, illustrating the monumental investment in public infrastructure and the future of Los Angeles. The project's integration of smart technology systems for maintenance and operation sets new standards for public transportation. Let's investigate the Tokyo Bay Aqua Line project next, which is located in Japan. This innovative mega-project, completed in 1997 after almost a decade of construction and costing nearly $11 billion, spans 15.1 kilometers and merges the infrastructure of both tunnel and bridge into a seamless transport artery. The Aqua Line begins with a 4.4-kilometer bridge stretching from Kawasaki and transitions into a 9.6-kilometer undersea tunnel, making it the world's fourth longest one. The two sections meet at an artificial island known as Yumahataru, a 650-meter diameter structure that serves as both a ventilation shaft and an entertainment complex. A project of this magnitude presented considerable engineering challenges. To manage the underwater construction, the teams utilized the world's largest shield tunneling machines, which bored through the seabed while simultaneously reinforcing the walls with high-strength concrete segments. The tunnel was divided into several watertight sections to minimize flooding risks. Meanwhile, constructing the bridge required innovative solutions to address seismic concerns, given Japan's notorious earthquakes. Engineers designed flexible bridge piers to withstand tremors, while shock absorbers were embedded in the structure to minimize damage. The project's complexity also meant securing permits from multiple government agencies, while ensuring minimal impact on the marine ecosystem. The result is a structure that has drastically shortened the travel distance between Kawasaki and Kisarazu by over 70 kilometers. In terms of size, the Tokyo Bay Aqua Line is comparable to almost 200 football fields and handles around 32,000 vehicles daily. It's time to move over to Switzerland for an incredibly expansive collider project. The Large Hadron Collider, straddling the Swiss-French border near Geneva, represents one of the most audacious experiments in the history of science. With a project cost of $4.75 billion, this behemoth is not only the world's largest particle accelerator, but also a centerpiece in our quest to unravel the mysteries of the universe. Envision a circular tunnel, 27 kilometers in circumference, buried up to 175 meters underground. This isn't just any tunnel, it's a superhighway where protons travel at nearly the speed of light, colliding 600 million times per second. These collisions generate temperatures 1,000,000 times hotter than the center of the sun, momentarily recreating the conditions of the universe a fraction of a second after the Big Bang. The project's construction required the precision of aligning its two beams to within a hair's breadth over its 27-kilometer length. The magnets used to steer the beams are superconducting and must be cooled to minus 271.3 degrees Celsius. In 2012, the collider proved its worth by confirming the existence of the Higgs boson, often called the God particle. This elusive particle, key to the theory that explains how other particles get their mass, had remained only a theory for nearly 50 years until the collider's experiments confirmed it. But the Large Hadron Collider isn't just about particle physics. It's a hub of innovation that's propelled advances in fields like medical imaging and computing. For instance, technologies developed at CERN have led to improvements in PET scans, a crucial medical diagnostic tool. It's time to move over to Boston now for the Green Line Extension megaproject. This extension aims to enhance public transit services by connecting the densely populated but underserved areas of Somerville and Medford to the existing subway network, thereby increasing accessibility to central Boston. Launched with major construction efforts ramping up around 2018, the GLX project completed in 2023. The project's budget, initially estimated at $2 billion, saw an increase to nearly $2.3 billion due to unforeseen construction and environmental challenges. Spanning approximately 4.7 miles, the GLX adds 7 new stations along 2 branches, one terminating at Union Square in Somerville and the other at Tufts University in Medford. These new tracks and stations are expected to serve about 45,000 riders daily, significantly easing traffic congestion and reducing commute times in these high-density corridors. The workforce required for this mammoth project varied throughout its phases, involving up to 1,000 construction workers and engineers at peak times. One of the most critical problems the GLX project addresses is the reduction of vehicle emissions by providing a reliable and efficient public transit alternative, thereby contributing to the state's environmental goals. In terms of construction, the GLX employed advanced methods including the use of track-laying machines that allowed for faster, more efficient installation of rail lines. This project also involved substantial upgrades to existing infrastructure, such as the improvement of bridges and roads along the extension path, ensuring that the new service would be integrated smoothly with minimal disruption. Challenges encountered during the GLX project included managing complex logistics in densely populated areas, mitigating noise and disruption to local communities, and addressing cost overruns and delays, which were exacerbated by the pandemic. We have to travel over to Alberta next for the Trans Mountain Pipeline Expansion Project next. Launched in 2017, this monumental project is designed to twin the existing pipeline, increasing the capacity from 300,000 to 890,000 barrels of oil per day, ensuring Canada's position as a leader in the global oil market. Spanning a staggering 1,150 kilometers, this pipeline cuts through mountains and rivers, connecting Alberta's rich oil fields to the world. The scale is immense, involving thousands of workers, each dedicated to meticulously constructing a route that respects both the environment and the communities it passes through. With a budget now estimated at 12.6 billion Canadian dollars, the project's costs have escalated due to rigorous environmental safeguards and the strategic implementation of cutting-edge construction technologies designed to minimize ecological impact. These methods include horizontal directional drilling, a technique that allows the pipeline to pass beneath sensitive ecological areas and major obstacles like the Fraser River without disturbing the surface. But the journey has not been without its hurdles. Navigating through one of the world's most rugged terrains, the project faces the relentless challenge of mountainous landscapes and the strictest environmental scrutiny. The line must also withstand the threats posed by seismic activity, demanding that every segment of the pipeline not only meets but exceeds safety standards. The expansion is more than just an engineering feat. It solves the critical problem of landlocked Alberta's oil market access. By providing a direct link to the Pacific coast, it opens up lucrative Asian markets, potentially increasing Canada's GDP by billions of dollars and ensuring thousands of jobs for Canadians for years to come. In terms of sheer volume, the amount of steel used in the pipeline is equivalent to building 60 Eiffel Towers. Let's investigate the Gran Gasoducto del Sur next. This is a major infrastructure project designed to transport natural gas from Venezuela to Argentina, passing through Brazil. This ambitious project aims to enhance regional energy integration and provide a reliable supply of natural gas to support economic growth and development in South America. Construction of the Gran Gasoducto del Sur began in 2015, with the project expected to span approximately 5,000 miles. The pipeline is designed to transport up to 50 million cubic meters of natural gas per day, providing a crucial energy source for industrial, commercial, and residential use. The pipeline will connect key natural gas fields in Venezuela with major consumption centers in Brazil and Argentina, enhancing energy security and reducing reliance on imported fuels. One of the significant engineering challenges of the Gran Gasoducto del Sur is the diverse terrain it traverses. The pipeline route includes dense forests, mountainous regions, and river crossings, requiring advanced engineering solutions and extensive environmental assessments. The project incorporates state-of-the-art technology for pipeline construction and monitoring, ensuring the safety and reliability of the gas supply. The total cost of the Gran Gasoducto del Sur is estimated at $23 billion. The project is expected to generate substantial economic benefits, including job creation, increased energy supply, and enhanced regional cooperation. Environmental and social considerations are integral to the Gran Gasoducto del Sur project. Comprehensive environmental impact assessments were conducted to minimize the impact on local ecosystems and communities. The project includes measures to protect biodiversity, manage water resources, and engage with local communities to address their concerns and ensure their participation in the project's benefits. Let's move over to the Netherlands next for the highly impressive North-South Line Metro project. The new metro line, which runs from the northern to the southern parts of Amsterdam, provides a fast and efficient transport option for residents and visitors. The project involved the construction of new tunnels, stations, and tracks, significantly enhancing the city's transport network. Construction of the North-South Line began in 2002, with completion achieved in 2018. The project represents a substantial investment, estimated at around $3.1 billion. One of the primary challenges of the project was tunneling through the soft and waterlogged soil of Amsterdam, which required advanced engineering techniques and machinery. The North-South Line features 9 new stations, each designed with modern amenities and advanced technology. Sustainability is a key focus of the North-South Line project. The new metro line is powered by renewable energy, and the stations are equipped with energy-efficient systems, such as LED lighting and advanced heating and cooling technologies. One of the significant challenges of the project was maintaining the city's normal operations while construction was underway. To minimize disruption, the project team employed a phased construction approach, allowing sections of the metro line to be completed and open to the public while work continued on other sections. This approach requires careful planning and coordination to ensure that the project stays on schedule and within budget. The North-South Line has significantly improved public transport in Amsterdam, providing a fast and reliable connection between the northern and southern parts of the city. The new metro line has reduced travel times and eased congestion on other transport routes, contributing to the overall development of the city's transport network. Another country that's investing a lot into travel projects is India. They are building the Mumbai Coastal Road project, poised to redefine urban mobility in one of India's most populous cities. This ambitious project, with an estimated budget of over $1.5 billion, represents a significant leap towards alleviating traffic congestion and enhancing connectivity within Mumbai. Currently under construction, the coastal road will stretch 29.2 kilometers along Mumbai's western coastline, linking the Marine Lines area in the south to the Kandivali neighborhood in the north. Designed to include 8 lanes, the project integrates a combination of tunnels, bridges, interchanges, and viaducts. A notable feature of this project is the 3.4-kilometer twin tunnel, expected to be the longest of its kind in India, running beneath Gurgaon Chowpatty and Malabar Hill. This engineering marvel is designed to expedite travel times while preserving the scenic coastline. Projected for completion by 2025, the Mumbai Coastal Road aims to significantly reduce travel time for commuters, cutting the current 3-hour drive down to an estimated 40 minutes. Let's visit the Delaware Aqueduct, renowned as the world's longest continuous underground tunnel. Spanning an extraordinary 85 miles from the Rondout Reservoir in the Catskills to the Hillview Reservoir in Yonkers, New York, this aqueduct is crucial, supplying about 50% of New York City's fresh water. It was constructed between 1939 and 1945, burrowing as deep as 1,500 feet beneath the Hudson River. Designed to transport roughly 600 million gallons of water daily, The aqueduct features a 13.5 feet diameter, lined entirely with concrete to ensure efficient water flow and structural integrity. The construction required the mobilization of 17,000 workers who faced the formidable challenge of excavating through solid rock and managing high-pressure water ingress. Innovative for its era, the project utilized both tunnel boring machines and traditional drilling and blasting methods. Operating under pressures that can exceed 200 psi, the structural design of the aqueduct was a complex undertaking. Engineers had to develop special concrete formulations and construction techniques to cope with the pressures equivalent to being 460 feet underwater, initially costing about $160 million in 1940, which is about $2 billion today when adjusted. The Delaware Aqueduct's financial implications were significant. Beyond the immense cost, the project stirred environmental and social controversies, including the displacement of communities and substantial ecological impacts due to its construction. In terms of maintenance, the aqueduct has not been without its problems either. It suffers from leaks that lose up to 35 million gallons of water per day, necessitating a major repair initiative. A $1 billion project is currently underway, which includes the construction of a 2.5-mile bypass tunnel around the most severely affected section. Let's transition to another underwater project that is connecting cities, called the Busan Geoje Fixed Link. Spanning an impressive length of 8.2 kilometers, this fixed link connects the bustling city of Busan with the scenic island of Geoje in South Korea, serving as a vital artery that significantly reduces travel time. Constructed at a cost of approximately $800 million, the project was completed in 2010 after 5 years of relentless work. The fixed link is a hybrid structure comprising both bridges and underwater tunnels, ingeniously designed to navigate the challenges posed by the area's deep waters. The centerpiece of this engineering feat is a 3.7-kilometer immersed tunnel, one of the longest of its kind in the world, which plunges beneath the sea to allow ships to pass unimpeded above. Despite its successes, the project was not without its challenges. Environmental concerns were raised regarding the impact on the marine ecosystem, leading to stringent measures being implemented to mitigate damage. Financial obstacles also loomed large, with debates on the project's cost-effectiveness and the burden on public resources sparking rigorous discussions. We have to travel to Australia next for the Forestfield Airport Link megaproject. This visionary public transport project in Perth, Australia, is set to transform how travelers and residents move around the city. Initiated in 2016 and completed in 2022, this ambitious project aims to seamlessly connect Perth's eastern suburbs to the city center and the airport, enhancing mobility and spurring economic growth. Spanning a total of 8.5 kilometers, the link features a twin-bore tunnel and 3 new stations, each designed with unique architectural elements that reflect the local heritage and landscape. The cost of this strategic initiative is pegged at approximately 1.86 billion Australian dollars, making it one of the highest investments in Western Australia's public transport system in decades. One of the remarkable aspects of this project is the use of tunnel boring machines. These technological marvels, affectionately named Grace and Sandy, have been instrumental in excavating the tunnels. Each machine is over 130 meters long and weighs more than 600 tons, capable of tunneling through up to 20 meters of earth per day. The construction has faced numerous challenges, notably the complex geological conditions that include sandy and water-bearing soils, which are particularly tricky to navigate. This required innovative tunneling techniques and state-of-the-art waterproofing solutions to ensure the structural integrity and longevity of the tunnel. Each station will also feature artworks that celebrate the cultural and natural heritage of the area, creating not just transit points but destinations that offer a sense of place and community. The Sydney Metro expansion is an ambitious endeavour designed to dramatically enhance the public transportation network in Australia's largest city. This project extends the metro service into the Greater Western Sydney area and includes the new Sydney Metro City and Southwest Line. This expansive network will add 66 kilometers of new metro rail. The project comprises 18 stations, which when laid end-to-end, would stretch nearly 5 kilometers, long enough to cover the Golden Gate Bridge 1.5 times. The construction of this project involves more than 50,000 individual tasks and the cooperation of over 5,000 workers at peak times. The budget for this monumental infrastructure project is estimated at $10 billion, making it one of the largest public transportation investments in recent Australian history. Key features of the expansion include twin 15.5-kilometer tunnels, which are among the longest railway tunnels in the world. To put that into perspective, this is more than 3 times the length of the Channel Tunnel that runs under the Thames in London. The stations themselves are feats of engineering designed for efficiency and integration with the city's existing transport fabric. Barangaroo Station, for example, is constructed 42 meters below ground level, which is as deep as a 12-story building is tall. Sydney Metro's new rolling stock will also set a new standard for public transport in the region. Trains are designed to be fully automated and driverless, featuring real-time route information and the capacity to move 40,000 passengers per hour in each direction, which matches the throughput of some of the busiest metro systems in the world, like those in Paris. But we have to travel to France next, where the LGV Sud Europe Atlantique project represents a major leap in the country's high-speed rail network. Initiated in 2011 and completed in 2017. It extends the existing high-speed line from Tours to Bordeaux, spanning approximately 188 miles. This new section of the line significantly reduces travel times, cutting the journey from Paris to Bordeaux to just over 2 hours. One of the most impressive aspects of the LGV project is the scale of its construction. With an investment of around $8 billion, the project involved extensive engineering work, including the construction of over 400 engineering structures such as viaducts, bridges, and tunnels. The route traverses diverse landscapes, from rolling countryside to urban areas, necessitating innovative solutions to minimize environmental impact and disruption to local communities. A notable feature of the LGV line is its advanced rail technology. The line supports trains traveling at speeds of up to 200 miles per hour, making it one of the fastest rail lines in Europe. This high-speed capability is achieved through the use of state-of-the-art track design and cutting-edge signaling systems, ensuring both speed and safety. The environmental considerations of the project were paramount. Extensive environmental impact assessments were conducted, and measures were taken to protect local wildlife and natural habitats. Additionally, the project included reforestation initiatives and the restoration of natural landscapes affected by the construction. Beyond its engineering feats, the LGV project has had a profound socio-economic impact. By dramatically reducing travel times, it has enhanced the accessibility of southwestern France, promoting regional development and economic growth. The construction phase of the project provided a significant boost to the local economy, generating thousands of jobs and supporting numerous businesses. For the next Asian megaproject, we have to travel to Japan. This is where the Chuo Shinkansen project is located, a maglev marvel that links Tokyo to Nagoya at mind-boggling speeds of up to 500 kilometers per hour. This high-speed rail megaproject aims to revolutionize intercity transport, slicing travel time between the two cities from 100 to a mere 40 minutes. The Chuo Shinkansen is poised to become the world's fastest land transportation system, delivering passengers across 286 kilometers with unparalleled efficiency. The engineering genius behind this project lies in the magnetic levitation technology, which eliminates the friction of traditional rail systems by suspending the train in midair using powerful superconducting magnets. This innovative approach, which has been in development since the 70s, propels the train forward smoothly and quietly. But the path from concept to completion has been anything but straightforward. The construction process requires massive excavation work, as over 85% of the line will be underground or within tunnels, including the longest rail tunnel in Japan, stretching a remarkable 25 kilometers. The entire project has an estimated price tag of $50 billion for the Tokyo-Nagoya stretch alone, making it one of the costliest rail projects ever conceived. Over 15,000 workers are on site daily, boring through some of Japan's most challenging terrain, including the Central Alps. When fully operational, the Chuo Shinkansen will accommodate up to 1,000 passengers per train, potentially transporting over 80 million passengers annually. It will also expand to reach Osaka in the project's second phase, providing an alternative to both air and road travel. In comparison to other global rail projects, the Chuo Shinkansen stands in a class of its own. Its technological ambition far surpasses high-speed lines in Europe or the United States, while its environmental considerations make it a template for future high-speed rail developments. Next up, we have to talk about one of the most expensive electrical projects in Europe, called the Viking Link project. This is an ambitious power connection project stretching over 760 kilometers between the United Kingdom and Denmark. Its primary aim is to enhance the security and sustainability of energy supply by enabling the transfer of up to 1,400 megawatts of electricity between the two countries, enough to power approximately 1.4 million homes. Initiated in 2020, this project is pivotal in fostering energy cooperation across borders. The construction involves laying submarine and underground cables from Revsing in Denmark to Bickerfen in Lincolnshire. These cables are engineered to withstand harsh marine environments and provide a reliable conduit for electricity over decades. The technology used in the Viking Link incorporates high-voltage direct current systems, which are more efficient over long distances than the more common alternating current systems. Addressing challenges such as environmental impact and technical complexities, the project required meticulous planning and consultation with marine biologists to minimize disruption to marine life. Additionally, engineers faced the technical challenge of routing cables through varied terrains, including the North Sea's challenging seabed. The project also incorporates cutting-edge converter stations at each end, which are crucial for converting electricity between DC used in transmission and AC used in domestic power grids. With a total cost of $1.92 billion, this project represents a major investment in sustainable infrastructure. But what about a massive dam megaproject? For that, we have to travel to the Ohio River, where the Almsted Locks and Dam project is located. This monumental undertaking, designed to replace aging infrastructure and modernize the waterway system, is crucial for the transportation of billions of dollars worth of goods annually across central U.S. This project, which officially completed in 2018 after over 30 years of planning and construction, spans across the river and involved an extraordinary financial investment of approximately $3 billion. The construction required the sustained effort of hundreds of engineers, technicians, and laborers over several decades, underscoring the project's scale and complexity. The Almsted project replaced two older and less efficient facilities, Locks and Dams 52 and 53, which had become increasingly unreliable, causing significant delays in river traffic and logistical inefficiencies. The new structure consists of a navigational pass and two parallel 110 feet by 1,200 feet locks. This setup significantly eases the river traffic, allowing for the smooth passage of approximately 90 million tons of cargo yearly. One of the notable challenges of the Almsted Locks and Dam was its innovative construction method, specifically the use of in-the-wet technology. Unlike traditional dry dock methods, this technique involves assembling large modular sections of the dam on land, then floating them to their installation site on the river. The total amount of concrete used in the dam's construction would be enough to pave a sidewalk stretching from New York to San Francisco. A special feature of the Almsted Locks and Dam is its resilience to seismic activity. The region is near the New Madrid fault line, and as such, the structure was designed to withstand significant earthquakes, ensuring the long-term stability and safety of this critical infrastructure. The project's importance extends beyond just its immediate functionality. By improving the reliability and efficiency of the Ohio River as a navigational channel, the Almsted Locks and Dam also bolsters the economic viability of river transportation, which is significantly more fuel efficient and environmentally friendly compared to road and rail transport. Let's travel over to the next project, called the Evergreen Line. When the Evergreen Line opened its doors to the public in December 2016, it wasn't just unveiling a new set of tracks. It was laying down 11 kilometers of advanced rapid transit that now serves as a critical spine, connecting over 70,000 passengers daily. This $1.43 billion project showcases the sheer scale and ambition of modern infrastructure endeavors, employing state-of-the-art construction methods and technology. Constructing the Evergreen Line involved laying enough track to stretch across about 100 football fields placed end to end. Within this sprawling network, 6 new stations emerged, each designed with unique architectural elements reflecting the character of their respective neighborhoods, enhancing not just functionality but also community identity. The construction of this project was a monumental task involving more than 8,000 workers who came together to tackle a variety of complex challenges. One of the most significant feats was the boring of a 2-kilometer tunnel beneath Burnaby Mountain, a technical marvel in itself. This tunnel, crucial for connecting the two ends of the line, required one of the largest earth pressure balance tunnel boring machines used in North America. The machine, nicknamed Alice, represents the spirit of innovation and determination that fueled this project. Dealing with the diverse terrain of the region, from dense urban areas to the delicate ecosystems surrounding the mountain, posed its own set of challenges. Engineers and planners meticulously designed the route and construction phases to minimize environmental impact, which included preserving the local creeks and surrounding green spaces. But what about a country that got a brand new metro system? That's what happened with the Metro de Quito project. The metro line spans approximately 14 miles and includes 15 stations, connecting the southern and northern parts of Quito. Construction of the Metro de Quito began in 2013, and the project faced numerous challenges, including the city's complex geology and the need to preserve historical sites. The metro tunnels were excavated using tunnel boring machines, which allowed for precise and efficient tunneling while minimizing surface disruption. The use of the machines also ensured the protection of Quito's colonial-era buildings and other historical landmarks. The Metro de Quito is designed to accommodate over 400,000 passengers daily, significantly reducing the number of vehicles on the road and improving air quality. The metro system features modern trains equipped with the latest technology, including automated systems for safety and efficiency. The stations are designed to be accessible and user-friendly, with features such as elevators, escalators, and clear signage. One of the significant benefits of the Metro de Quito is the reduction in travel time. Commuters can travel from one end of the city to the other in approximately 34 minutes, compared to over an hour by car during peak traffic. This improvement in mobility is expected to boost economic activities and enhance the quality of life for Quito's residents. The total cost of the Metro de Quito project is estimated at $2 billion, funded by a combination of national and international sources. The project has generated significant economic benefits, including job creation during the construction phase and increased commercial activities around the metro stations. Environmental sustainability is a key aspect of the Metro de Quito project. The metro system is powered by electricity, reducing greenhouse gas emissions and contributing to Quito's efforts to combat climate change. It's time to talk about the Jakarta-Bandung high-speed rail in Indonesia, which is an ambitious project aimed at significantly reducing travel time between Jakarta and Bandung from over 3 hours to approximately 40 minutes. With an estimated cost of $6 billion, this project is Indonesia's first high-speed rail venture. Construction began in 2016, focusing on advanced construction techniques and technologies. One of the primary engineering challenges was the diverse terrain between Jakarta and Bandung, necessitating the construction of numerous bridges and tunnels. The line features 13 tunnels, including the Welini Tunnel, the longest at 4.5 kilometers. The construction of these tunnels employed tunnel boring machines, essential for efficiently and safely excavating through varied geological conditions. The rail line is designed to accommodate speeds of up to 250 kilometers per hour, requiring the use of high-strength materials and precision engineering to ensure safety and stability. The tracks are laid on a slab track system, which provides greater durability and requires less maintenance compared to traditional ballast tracks. This system involves laying the rails on concrete slabs fixed in place with high-precision techniques to maintain the alignment and smoothness required for high-speed travel. A significant challenge faced during the construction was minimizing the impact on densely populated areas along the route. To address this, elevated tracks and viaducts were constructed in several sections, reducing the need for land acquisition and minimizing disruption to local communities. Another critical aspect of the construction process was ensuring the rail line's resilience to seismic activity. Indonesia is located in a seismically active region, so the design incorporates earthquake-resistant features. These include flexible track systems and shock-absorbing materials that can withstand significant ground movement without compromising the rail line's integrity. Logistics played a crucial role in the project's success, given the scale and complexity of the construction. Materials and equipment had to be transported to various construction sites along the 142.3-kilometer route. This required a well-coordinated supply chain and efficient transportation network to ensure timely delivery and minimize delays. But that's not the only impressive travel megaproject France is working on, because they also have the Lyon-Turin high-speed rail. This project is a groundbreaking endeavor set to revolutionize transportation between France and Italy, signifying a major leap in European rail infrastructure. With a budget estimated at over 26 billion euros, the project's centerpiece is the Mont Cenis base tunnel, stretching 57.5 kilometers, poised to become one of the world's longest rail tunnels. This tunnel will significantly reduce the Lyon to Turin travel time, aiming to shift a substantial portion of freight and passenger traffic from road to rail, thereby decreasing carbon emissions and traffic congestion. Scheduled for completion in 2030, the Lyon-Turin high-speed rail will extend approximately 270 kilometers, incorporating state-of-the-art technology and engineering. Upon completion, the rail line is expected to accommodate speeds of up to 220 kilometers per hour, slashing the Lyon-Turin journey to just under 2 hours. Opened in 2007, it spans an impressive 18 kilometers, or 11 miles, making it one of the longest mountain tunnels globally. This dual-tube tunnel cuts through the heart of Jiangnan Mountain, reducing the travel time between Xi'an and Anqing from 4 hours to just under 2 hours. Excavating at depths of up to 1,640 feet beneath the mountain peaks, the tunnel presented unique geological challenges. The construction teams encountered a range of difficult conditions, from soft rocks and high groundwater inflow to hazardous gas emissions, each requiring bespoke solutions. The project's cost was estimated at approximately $470 million. One of the unique aspects of the Zhongnanshan Tunnel is its ventilation system. Given the tunnel's length and depth, maintaining air quality was paramount. The system is a pioneering effort in China for long tunnels, involving large ventilation towers that extract air from the center of the tunnel, ensuring the safety and comfort of motorists. This contrasts sharply with many older tunnels where simpler and less effective ventilation systems were implemented. Construction of the tunnel also set benchmarks in environmental conservation. The project included comprehensive measures to prevent damage to the local ecosystem, including relocating certain plant species and creating artificial waterways to redirect water flows altered by construction. In the tunnel's early years, it experienced problems with water leakage and ice formation in winter, posing risks to traffic safety. These problems were addressed through the retrofitting of the drainage system and the installation of an ice warning and response system, which have been critical in minimizing accidents and maintaining clear passage during the winter months. While underwater tunnels are usually used for mobility, Canada is utilizing them for something else with their Seymour Capilano water filtration project. Nestled in the verdant landscapes of British Columbia, Canada, the tunnel is an engineering marvel designed to ensure the provision of clean, safe drinking water to the Vancouver metropolitan area. This project is distinguished by its expansive network of tunnels, stretching over 7.1 kilometers, which serve as conduits for transferring water between the Seymour Reservoir and the Capilano Reservoir. Constructed at a cost of over 600 million Canadian dollars, the project underscores the critical importance of sustainable water management in urban planning. The construction process showcased a blend of traditional tunneling methods and modern technological innovations. 2 massive tunnel boring machines were deployed, each weighing over 1,000 tons, carving through the mountainous terrain with precision. The project became operational in May 2010, and ever since it has been a vital part of the region. Let's move over to the United States next, where the Central Arizona Project is located. This engineering marvel stretches over 336 miles and is designed to bring about 1.5 million acre-feet of Colorado River water annually to central and southern Arizona. Initiated in 1973 and completed in 1993, this monumental project has been pivotal in addressing water scarcity issues in one of the driest regions of the country. Constructed at a cost of over $4 billion, the project is the largest single resource of renewable water supplies in Arizona. It includes a series of aqueducts, tunnels, pumping stations, and pipelines. It starts at Lake Havasu and ends 14 miles south of Tucson at the San Xavier Indian Reservation. The project features more than a dozen pumping stations which collectively lift the water 2,900 feet vertically, equivalent to a skyscraper nearly twice as high as the Empire State Building. To push water across such a vast stretch of desert, the project uses about 2.8 billion kilowatt hours of power annually, which is about the same amount of energy needed to power approximately 250,000 homes for a year. Building the Central Arizona project was an enormous challenge, primarily due to the harsh desert environment and the need to maintain ecological balance. Special construction methods were employed, including blasting through rock and the construction of the Waddell Dam, which had to be raised to increase the capacity of Lake Pleasant. Let's journey to Vietnam next, where the North-South Railway, a modern reincarnation of the historic Reunification Express line, is Vietnam's most ambitious rail infrastructure project. Stretching over 1,700 kilometers from Hanoi in the north to Ho Chi Minh City in the south, this project aims to modernize and expand Vietnam's railway system. At an estimated cost of $58.7 billion, this megaproject will feature high-speed rail capable of whisking passengers at speeds up to 350 kilometers per hour. The project includes 23 stations and is divided into two primary segments, each built simultaneously. The high-speed rail system will ride on a standard gauge track supported by pre-stressed concrete sleepers and bridges that cross Vietnam's diverse terrain. As much of the line traverses challenging landscapes, extensive tunneling is necessary, particularly in the mountainous central regions. Engineers have already identified the need for over 30 tunnels totaling nearly 50 kilometers. One of the project's central challenges lies in navigating the densely populated areas while minimizing land acquisition issues. Innovative design measures, like elevated tracks and noise barriers, have been adopted to mitigate disruption. Advanced construction methods, such as incremental launching and cantilever segmental techniques, ensure that bridges and tunnels are built efficiently and safely. Beyond its transformative speed, the North-South Railway will significantly reduce carbon emissions by diverting traffic from roadways. This greener alternative could reduce Vietnam's transport emissions by millions of tons annually. But how about one of the most impressive underground rail projects in Europe? The Jubilee Line extension initiated in the mid-1990s and opened in phases between 1999 and 2000. This extension added 16 kilometers to the Jubilee Line, stretching from Green Park to Stratford and including 11 new stations. This project tackled the acute need for improved transit solutions in underserved areas of East London and supported the regeneration of numerous boroughs along its route. Each station is uniquely designed, with Canary Wharf Station being one of the largest, enclosed in a vast glass dome and supporting a daily footfall in the hundreds of thousands. The extension was not just about adding track. It involved sophisticated engineering challenges, particularly in constructing deep-level tunnels beneath some of the most densely developed parts of the city. A workforce of over 3,000 people was engaged, with a peak of 2,000 workers underground during the height of construction. The logistics of moving such numbers in and out of confined spaces safely and efficiently was a testament to the meticulous planning and execution of the project managers. One of the most notable features of the Jubilee Line extension is its integration of art and architecture within the public transport system. Each new station features works by different artists, making the line a cultural tour as much as a transit route. On the technical front, the extension required laying down enough concrete to fill 30 Olympic-sized swimming pools and enough steel to build 2 Eiffel Towers. The challenges were manifold, including financial overruns and delays that pushed the final cost to $4.3 billion, a figure that reveals the complex nature of urban underground construction. The Kiruna mine is not only the world's largest iron ore mine, but also one of its most profound, with operations extending up to 1,365 meters below the surface. This mine, which has been operational since 1898, annually produces over 35 million tons of iron ore, dwarfing smaller operations like the Iron Mountain mine in California. Kiruna's expansive network covers an area of 174 square miles, making it larger than the well-known Carajás mine in Brazil. The mine's innovative use of automated drilling and haulage technology marks it as one of the most modernized mines globally. With over 310 miles of roads within the mine, Kiruna operates like an underground city. Its depth and scale necessitate a unique ventilation system capable of circulating approximately 1,200 cubic meters of air per second. The relocation of Kiruna's town due to mining-induced ground deformation is a distinctive aspect unmatched by any other mining project globally. This massive undertaking involves moving residential buildings and key infrastructures to a new site 3 kilometers east, ensuring the town's sustainability and the mine's expansion. The estimated cost of relocation tops €1 billion, highlighting the scale and economic impact of this project on the local community. The mine's strategic importance is underscored by its contribution to Sweden's economy, supplying over 90% of the iron ore produced in Europe. The Channel Tunnel, an engineering feat that bridged the UK and France beneath the English Channel, stands as a symbol of European unity and technological ambition. Completed in 1994 at a cost of £12 billion, this project was one of the most significant engineering projects of the 20th century. Spanning 50.45 kilometers, with 37.9 kilometers beneath the sea, the Channel Tunnel holds the record for the longest undersea portion of any tunnel in the world. The construction involved the use of 11 tunnel boring machines to carve through the chalk marl beneath the seabed. This Herculean task required unprecedented coordination between British and French construction teams. The tunnel comprises 3 separate tubes, 2 for rail traffic, and a smaller service tunnel that acts as an emergency escape route. The use of precast concrete linings to reinforce the tunnel walls was a critical component of the construction strategy, ensuring the tunnel's durability and safety. Today, the Channel Tunnel is a vital link for commerce and travel between the UK and continental Europe, facilitating the seamless transit of millions of passengers and tons of freight annually. Let's move over to the Spadina subway extension megaproject next, located in Toronto. Officially opened in December 2017, this project not only extended the western reach of the city's subway network, but also bridged the gap between Toronto and the York region, fostering an unprecedented level of accessibility across these bustling areas. The extension added 6 new stations along an 8.6-kilometer stretch, starting from Downsview Park all the way to the Vaughan Metropolitan Centre. The design and construction of these stations involved a collaboration among some of the world's most innovative architects and engineers, aimed at creating spaces that are not just transit nodes but also community hubs. The budget for this expansive project was initially set at $2.6 billion, but saw an increase to nearly $3.2 billion due to various challenges and complexities encountered during construction. These challenges included engineering hurdles such as tunneling near existing infrastructure, managing underground water flows, and coordinating with multiple contractors and stakeholders to keep the project moving forward smoothly. One of the most significant engineering feats was the use of tunnel boring machines, which carved through the earth beneath the city with precision. These machines played a pivotal role in creating the 6.4-kilometer twin tunnels that form the backbone of the extension. The project not only expanded the physical landscape of Toronto's subway system, but also addressed crucial urban issues like congestion and sustainable urban growth. By providing a reliable and efficient public transit option, the extension has significantly reduced traffic volumes on the busy highways and main roads, leading to a more environmentally friendly and less congested urban environment. Next up, it's time to travel over to Norway for the Oslo Central Station project. This development involves extensive upgrades to the station's infrastructure, including the construction of new platforms, tracks, and passenger facilities. The goal is to improve capacity, accessibility, and the overall passenger experience. Construction of the Oslo Central Station redevelopment began in 2018. and it's bound to be fully operational by the end of 2024. The project represents a significant investment, estimated at around $2 billion. One of the key features of the redevelopment is the expansion of the station's concourse, which will provide more space for passengers and reduce congestion during peak times. The project includes the construction of new platforms and tracks to accommodate the increasing number of trains and passengers using the station. Additionally, the redevelopment will feature new retail and dining options, creating a vibrant and dynamic environment for travelers. One of the primary challenges of the Oslo Central Station project has been maintaining station operations while construction is underway. To minimize disruption, the project team has implemented a phased construction approach, allowing sections of the station to remain open and functional throughout the redevelopment process. This approach has required careful planning and coordination to ensure that the project stays on schedule and within budget. The improved facilities and infrastructure will support the growing number of passengers using the station and contribute to the overall development of the city's transport network. Mponeng Gold Mine in South Africa reaches an astonishing 4 kilometers, or 2.5 miles into the Earth's crust. This operational depth exceeds that of any other mining venture globally, including the TauTona mine, which extends 3.9 kilometers underground. Mponeng, which means look at me in the local Sotho language, began its operations in 1986 under Anglo Gold Ashanti and has since become a symbol of extreme engineering challenges. The mine's shafts and tunnels cover an area so extensive that it descends below sea level at points, creating a unique set of geological conditions. To maintain operations at such depths, the mine circulates ice slurry to cool the ambient temperature, which can reach up to 55 degrees Celsius due to geothermal heat from the surrounding rock. Producing over 244,000 ounces of gold annually, Mponeng's output is significant compared to smaller gold mining operations, such as the Porcupine Mine in Canada. The high-grade gold ore body at Mponeng is accessed through a complex network of tunnels and shafts, requiring highly sophisticated drilling and blasting techniques that utilize automated loaders and dump trucks for ore extraction and transportation. Mponeng's vast network of underground development is supported by a workforce of around 5,600 people, each of whom must descend a vertical distance greater than the height of Mount Everest to reach the working faces. The operational complexities of Mponeng extend beyond simple excavation. The mine deals with rock bursts and seismic activity due to the immense pressures at depth. These geological stresses are managed through meticulous seismic monitoring and advanced rock bolting techniques. Financially, the development and continuous modernization of Mponeng have seen billions of rand invested over the decades, including substantial sums spent on refining the gold extraction and processing facilities. It's time to talk about the Mumbai-Ahmedabad high-speed rail, also known as the Bullet Train Project. Spanning approximately 508 kilometers or 316 miles, this high-speed rail link aims to reduce travel time between Mumbai, Maharashtra, and Ahmedabad, Gujarat, from the current 8 hours to a mere 2 hours and 7 minutes. Endowed with a generous loan from Japan, covering a significant portion of the project's estimated cost of $15 billion, the rail promises to be a marvel of modern engineering and technology. It will feature 12 stations along its route, utilizing Japan's renowned Shinkansen E5 series of bullet trains, which are celebrated for their punctuality, safety, and speed. The project's ambitious goal is to be operational by 2027, although this timeline could face adjustments due to challenges. How about a tunnel that has been connecting two countries for over 2 decades? Let's check out the Øresund Tunnel, which is part of the Øresund link that connects Denmark and Sweden, facilitating unprecedented connectivity between the two countries since its completion in 2000. This project, with a total cost of around 4 billion euros for the entire Øresund link, includes a bridge, an artificial island, and the tunnel itself, showcasing a blend of engineering ingenuity and cooperation across borders. Stretching 4 kilometers beneath the Øresund Strait, the tunnel complements the 8-kilometer bridge to form a comprehensive transport route. The construction of the tunnel employed the cut and cover method, where a trench was excavated on the seabed and prefabricated tunnel sections were then lowered into place. The Øresund Tunnel has significantly reduced travel time between Denmark and Sweden, bolstering economic ties and cultural exchange. time to travel to New York next, where the Fulton Center project is located. Officially opened in November 2014 after years of meticulous planning and construction, this transit hub exemplifies the renaissance of New York City's commitment to efficient and user-friendly public transportation infrastructure. Spanning a full city block, the Fulton Center integrates 5 subway stations and 9 subway lines, facilitating the seamless flow of over 300,000 daily commuters. This impressive facility was built at a cost of approximately $1.4 billion, a reflection of its scale and the complexity of its design. The center itself is an architectural marvel, highlighted by the sky reflector net, an awe-inspiring art installation and engineering masterpiece that anchors the facility. This structure is an integrated artwork composed of 952 aluminum panels that brilliantly capture and disperse natural sunlight throughout the atrium, reducing the need for artificial lighting and creating a vibrant, inviting atmosphere. The construction of the Fulton Center was laden with challenges, notably the need to modernize and interconnect a labyrinth of century-old subway stations and infrastructure without disrupting daily transit operations. This task required innovative construction techniques and the extensive use of computer simulations to plan and execute each phase of development meticulously. The main building spans about 180,000 square feet, with additional space connecting the various subway entrances, exits, and passageways extending further underground. The complexity of its design and the integration of so many transit lines make the Fulton Center comparable to other major transit hubs like Tokyo's Shibuya Station. One of the unique aspects of the Fulton Center's construction involved the historical preservation component. Part of the project included the restoration of the nearby Corbin Building, an 1889 landmark, which was intricately woven into the fabric of the new transit hub. Let's travel to Turkey for the first project, where the Marmara Rail Tunnel was launched back in 2013, linking the European and Asian parts of Istanbul. Spanning approximately 76.3 kilometers in total length, with 13.6 kilometers running under the sea, the Marmara project was developed with a budget of $4 billion. The construction of the Marmara Tunnel involved the deployment of some of the most advanced technologies and machinery in the field of civil engineering. A pivotal element of this project was the use of immersed tube tunnel technology, which involves the fabrication of tunnel sections on land, subsequently towed to the site, and meticulously lowered onto a prepared trench on the seabed. However, one of the most significant hurdles was the archaeological discoveries made during the excavation phases. Istanbul's rich history was laid bare as the project unearthed a treasure trove of historical artifacts, including Byzantine ships, which required meticulous archaeological examination. For the next project, journey with us into the heart of Toronto, where the Eglinton Crosstown Light Rail Transit project is reshaping the city's transit landscape. Spanning an ambitious 19 kilometers across Eglinton Avenue, the project was initiated in 2011 and completed in 2022. The project, budgeted at approximately $12 billion, underscores an epic saga of urban development, involving over 10,000 workers at its peak construction phases. The LRT line includes a significant underground section, spanning about 10 kilometers. Constructing this section involved the use of tunnel boring machines, each 10 meters in diameter. The scale of excavation is immense, with the project moving enough soil to fill the Rogers Center twice over. One of the project's major challenges has been managing construction while minimizing disruption to one of Toronto's busiest arteries. Advanced technologies and construction methods, such as the cut and cover and sequential excavation method, have been employed to ensure the structural integrity of the cityscape and the safety of its bustling populace. Each of the 25 stations on the line presents its own unique architectural and functional features, designed to not only accommodate but also enhance passenger experience with art installations and technology. This project also tackles the pressing issue of urban congestion by providing a reliable and efficient alternative to road transport. The Eglinton Crosstown LRT is expected to serve around 5,500 passengers per hour in each direction during peak times. Facing its fair share of hurdles, from labor strikes to engineering challenges due to the city's complex underground infrastructure, the project has navigated through delays and budget overruns, reflecting the all-too-common tale of large-scale urban transit projects. It's time to move over to Colombia next for the Orient Tunnel project. Designed to improve connectivity between Medellin and the Jose Maria Cordova International Airport in Riongro, this road tunnel is the longest in Colombia, spanning approximately 5.7 miles. Construction of the Túnel de Orient began in 2012 and was completed in 2019. The project involved extensive geological surveys and the use of advanced tunneling techniques to navigate the complex terrain of the Andes Mountains. The tunnel features dual bores, each accommodating 2 lanes of traffic, ensuring a smooth flow of vehicles and enhancing safety. One of the key benefits of the Túnel de Orient is the reduction in travel time. Prior to the tunnel's construction, the journey between Medellin and the airport took approximately 45 minutes to an hour, depending on traffic conditions. The tunnel reduces this travel time to just 18 minutes, providing a more direct and efficient route. The total cost of the Túnel de Orient project was approximately $300 million, funded by a combination of public and private investment. The project has generated significant economic benefits, including job creation during the construction phase and increased commercial activities once the tunnel became operational. Environmental and social considerations were integral to the project. The project also included measures to manage water resources, protect wildlife, and engage with local stakeholders to ensure that the benefits of the tunnel are shared with the surrounding areas. Let's move over to the United Kingdom, who are working on a project that will change British transportation, called the Lower Thames Crossing. This ambitious endeavor aims to construct a new 14.3-mile road link, including a 2.6-mile tunnel beneath the River Thames. Once completed, it will hold the distinction of being the longest road tunnel in the UK, significantly easing congestion on the existing Dartford crossing and enhancing connectivity between Essex and Kent. This project, with an estimated cost of around £8.2 billion, is designed not only to facilitate smoother traffic flow but also to spur economic growth by improving access to major ports and distribution centers. The Lower Thames Crossing is expected to handle approximately 4.5 million heavy goods vehicles in its first year, showcasing its critical role in supporting the UK's logistics and supply chain. Initially targeted for completion in the late 2022, the project's timeline has been adjusted, with the latest projections setting the opening date in the early 2032. We travel to France next for a gigantic canal megaproject called the Seine-Nord-Europe Canal. Designed to connect the Oise River at Campigny to the Dunkirk-Escaut Canal near Cambrai, this ambitious canal extends over 107 kilometers, providing a high-capacity waterway link between Paris and major northern European ports. Slated for completion in 2028, the canal aims to alleviate road and rail congestion by providing an eco-friendlier option for cargo transport. The canal is expected to support vessels up to 4,400 tons, double the capacity of most existing barges in the region. This increase not only maximizes cargo volumes, but also drastically reduces the environmental impact per ton of goods transported, aligning with broader European sustainability goals. The construction of the canal involves extensive earthworks, with an estimated 50 million cubic meters of soil to be excavated. This volume of soil is enough to fill the Great Pyramid of Giza approximately 5 times over. Furthermore, the project will include the construction of 3 massive locks, each capable of lifting vessels up to 13 meters high, akin to navigating a 4-story building vertically through water. In addition to the primary waterway, the project includes the creation of 55 structures, including aqueducts and bridges, to maintain the cross-connections between divided regions and to ensure that local ecosystems and communities remain intact. The workforce on this project is tasked not only with the physical construction, but also with implementing advanced hydroengineering techniques to manage the water flow and ensure safety during the canal's operation. One of the most innovative aspects of the Seine-Nord-Europe Canal is its incorporation of smart technology. The canal will feature automated lock systems and remote-operated bridges, enhancing operational efficiency and safety. This technological integration positions the canal as a future-proof infrastructure ready to handle the anticipated increase in automated and digital shipping processes. With a total cost of $5 billion, the Seine-Nord-Europe Canal is comparable in ambition and budget to other major infrastructure projects like London's Crossrail project. This laboratory is the deepest underground lab in the world, located approximately 2,400 meters beneath the surface in the Jinping Mountain. This staggering depth surpasses that of other well-known underground facilities like the Sanford Underground Research Facility in the United States. Established in 2010, the Jinping Lab is designed for the detection of dark matter particles and other low-background experiments that require protection from cosmic radiation. The depth provides an overburden of 6,700 meters water equivalent, the highest of any laboratory in the world. Spanning an area of 2,000 square meters, the laboratory's construction involved excavating approximately 80,000 cubic meters of rock, a volume that underscores the massive scale of this project compared to smaller scientific setups such as the Gran Sasso in Italy. One of the unique challenges faced during the construction of Jinping was managing the high water pressure prevalent at such depths, which necessitated the development of specialized waterproofing and pressure management systems. The Jinping Underground Laboratory is also a site of international collaboration, drawing scientists from across the globe to its deep earth cavern. Moreover, the laboratory's remote location and depth make it a logistical challenge, requiring the transportation of equipment and personnel through a single tunnel that connects the lab to the outside world. The California High-Speed Rail Project is an epic venture into modernizing transportation with an initial estimate of around $33 billion that has since soared past $100 billion. Designed to connect the state's major urban centers, such as San Francisco and Los Angeles, with speeds capable of reaching 220 miles per hour. The project aims to slash travel times to under 3 hours across approximately 800 miles of track, projected to be the first of its kind in the country. The high-speed rail's completion date has been a moving target, currently anticipated for 2033. This timeline reflects the project's vast scope and the intricate engineering challenges it faces, including the construction of over 36 miles of tunnels through the Tehachapi and San Gabriel Mountains. An exemplar of sustainable transportation, the rail project is committed to operating on 100% renewable energy, with stringent environmental protections integrated into its development to minimize impacts on natural habitats. Despite facing financial scrutiny and logistical obstacles, such as securing adequate funding and navigating the complexities of state and federal regulations, the California High-Speed Rail continues to push forward. Let's travel to the Netherlands next for one of the most impressive underwater projects on the list so far. The Western Scheldt Tunnel, completed in 2003 at a cost of approximately €750 million, is not just a passage but a lifeline connecting the regions of Zeeuws-Vlaanderen and South Beveland, and significantly reducing travel time in the area. Spanning an impressive 6.6 kilometers, the Western Scheldt Tunnel holds the title of the longest tunnel in the Netherlands. Constructed using the immersed tube method, it consists of segments that were meticulously built on land and then submerged and connected beneath the Scheldt River. This construction approach required precision and innovation, including the use of GPS technology to ensure exact alignment of the tunnel sections. Located in Lead, South Dakota, the Sanford Underground Research Facility is a pinnacle of science, situated a breathtaking 4,850 feet below the surface. This facility, which has repurposed the former Homestake gold mine, now serves as a forefront for scientific exploration shielded from cosmic interference. The transformation from a bustling gold mine to a sophisticated scientific research hub required an investment of over $600 million. At its operational peak, the Homestake mine produced approximately 40 million ounces of gold. The mine's extensive network of tunnels, which total over 370 miles, provides the necessary infrastructure for the project's deep underground science laboratories. The project initially faced significant opposition due to concerns over environmental impact and the stability of old mine workings. findings. There were fears about water contamination and surface subsidence, which led to stringent regulatory reviews and the implementation of sophisticated water treatment facilities. The facility now houses multiple laboratories, where over 500 scientists from around the world conduct experiments. The depth of the facility provides over 4,850 feet of rock cover, which effectively shields the laboratory from about 99.5% of cosmic radiation that would otherwise interfere with sensitive experiments. But what about a massive hydropower project? The Kherat Hydropower Project, a linchpin in the ambitious China-Pakistan economic corridor, marks a monumental stride in sustainable energy development between two nations. Nestled on the Jhelum River in the Punjab region between Pakistan's Kotli and Rawalpindi districts, this hydroelectric powerhouse is engineered to harness the untapped kinetic energy of flowing water to meet burgeoning energy needs. Initiated in 2015, the Kherat hydropower plant boasts a formidable capacity of 720 megawatts. This vast output is enough to provide over 5 million Pakistani homes with clean, renewable energy, significantly reducing the country's reliance on fossil fuels and combating the chronic power shortages that have hampered its economic growth. Constructed at a cost of approximately $1.74 billion, the project represents a profound investment in the infrastructure and future of energy in Pakistan. The scale of the construction effort is immense. At its peak, the project employed over 3,000 workers from both local communities and international experts, melding diverse skills to create a marvel of modern engineering. The project has involved excavating approximately 16 million cubic meters of earth and rock, enough to fill the Great Pyramid of Giza twice over. Furthermore, the amount of concrete poured to create the dam and powerhouse could pave a two-lane highway stretching over 60 kilometers. One of the most innovative aspects of the Kherat hydropower project is its environmental and social governance model. The project includes extensive fish passageways to ensure the protection of aquatic life, reflecting a commitment to biodiversity. However, constructing a project of this magnitude has not been without challenges. The engineering team has faced formidable logistical hurdles, including the transportation of heavy machinery through narrow mountain passes and managing the environmental impact on the Jhelum River's delicate ecosystem. It's time to go to Germany next, where Stuttgart 21 is being constructed. This project is a visionary rail and urban development project that fundamentally transforms Stuttgart's transport infrastructure and urban landscape. Initiated with construction in 2010, Stuttgart 21 is one of the most complex rail projects in Europe. It involves the excavation of 57 kilometers of new tunnels and the construction of 25 kilometers of new rail lines. The scale of earth moved in this project is staggering, enough to fill several thousand Olympic-sized swimming pools. This involves intricate engineering to handle and dispose of materials while ensuring stability for new and existing structures. Additionally, the project includes the redevelopment of 100 hectares of land in the city center, which will provide space for new homes, parks, and commercial areas once the rail lines are underground. The project has faced numerous challenges since its inception, including public protests and escalating costs. Originally estimated at around $4.5 billion, the budget has since ballooned to approximately $9.8 billion, making it one of the most expensive infrastructure projects in Europe. The increase in costs and the time required to manage such a massive undertaking have been points of contention and public debate. Despite these challenges, the benefits of Stuttgart 21 are projected to be significant. The new station will reduce travel times, increase train capacity, and improve connectivity between Stuttgart and major European cities. It's expected to enhance local and regional economic development and reduce traffic congestion in Stuttgart's city center. Approximately 5,000 workers are involved in this project, employing cutting-edge construction techniques and technologies. For instance, the use of slab track, a type of railway track that provides a consistent and stable base, is a key feature in modernizing the railway system. Comparatively, the total cost of $9.8 billion reflects a financial scale similar to that of constructing the new Terminal 5 at London's Heathrow Airport, underscoring the significant investment required for state-of-the-art infrastructure projects. Overcoming the physical and economic divide between Hong Kong and Zhuhai, This project was completed in October 2018, consisting of a series of bridges and tunnels spanning approximately 55 kilometers, making it one of the longest sea-crossing structures in the world. With a budget exceeding $18.8 billion, the project is designed to facilitate the flow of people and goods, strengthening connectivity and economic integration within the Pearl River Delta region. At the heart of this colossal structure is a 6.7-kilometer underwater tunnel, descending up to 40 meters below the sea level, seamlessly connecting two artificial islands. This tunnel was a critical solution to avoid disrupting the busy maritime lanes in the Pearl River estuary. The construction of the tunnels required innovative engineering techniques, including the use of immersed tube tunnel methods for the underwater sections. Let's travel to Chennai, the bustling capital city of Tamil Nadu, India. Here the Chennai Metro has emerged, which is rewriting the narrative of urban mobility in one of India's most dynamic cities. With a total network length of 54.15 kilometers and 41 stations spanning 2 corridors, this metro system is a lifeline connecting neighborhoods and industrial areas. Constructing this network was no easy feat. With a budget of over $3 billion, the project demanded cutting-edge construction techniques. Engineers and workers overcame enormous challenges posed by Chennai's complex geology, including loose alluvial soil and high groundwater levels. The team employed advanced tunnel boring machines for the underground stretches and meticulously precast concrete segments for elevated tracks. Some stations, such as the futuristic underground government estate, are constructed at dizzying depths of up to 23 meters below ground. The entire system was designed to cater to up to 700,000 passengers daily, reducing road congestion and air pollution across Chennai. The benefits of the Chennai Metro are not only immediate, but also strategic. As India's fifth largest urban agglomeration, Chennai needed an efficient transportation network to alleviate severe traffic snarls and boost economic productivity. Its sheer scale is comparable to other Asian transit networks, like the Bangkok BTS. However, the Chennai Metro stands out for its ambitious Phase 2 expansion plan. This phase will add 118.9 kilometers, turning Chennai Metro into one of the largest metro networks in India. Next up, we have to look at a project that's located in between Denmark, Sweden, and Germany. The Kriegers Flak offshore wind farm stands as a towering testament to Europe's commitment to renewable energy. With 72 turbines spinning over an area of 132 square kilometers, this wind farm is a crucial step toward achieving sustainability on a grand scale. The construction of Kriegers Flak began with the dual aims of enhancing energy production and reducing carbon emissions across the region. Upon its completion in 2021, it became one of the largest offshore wind farms in the world, boasting a capacity to generate 600 megawatts of power. This is enough energy to supply approximately 600,000 households annually, significantly impacting the region's energy dependency on fossil fuels. The installation of each turbine at Kriegers Flak was a meticulous process, involving specialized ships capable of handling the enormous weight and size of the components. Each turbine reaches up to 188 meters in height, nearly as tall as the Gherkin in London. A unique feature of Kriegers Flak is its role in supporting biodiversity. Artificial reefs were created using materials from the construction to promote marine life in the Baltic Sea, showcasing an innovative approach to environmental stewardship within an industrial project. Financially, the wind farm represents a significant investment in green technology, with a total cost of $1.4 billion. This investment underscores the economic scale of transitioning to renewable energy sources, comparable in cost to constructing major infrastructure like the new Queensferry crossing in Scotland. Moreover, Kriegers Flak serves as a critical junction for power connectivity in Europe. It includes an innovative feature that allows it to serve as an interconnector between Denmark and Germany, not only generating electricity but also facilitating energy trade between countries, enhancing grid stability and supply security across borders. Carving a 20-kilometer tunnel directly through the heart of the Andes Mountains and completed in 2006. This project represents one of the most ambitious underground endeavors globally, not just for its length but for its profound impact on the region's ecology and economy. Initiated to address severe water scarcity on Peru's arid Pacific coast, the tunnel channels water from the Huancabamba River on the Atlantic side of the Andes to the Pacific side. This engineering marvel plunges as deep as 2,000 meters below the mountain peaks, which is nearly 4 times deeper than the Channel Tunnel. The depth and complexity of tunneling through such diverse geological formations make the Almos Tunnel a standout project, far surpassing simpler ventures in both scale and technical challenges. Costing approximately $500 million, this project deployed one of the world's largest tunnel boring machines, nicknamed the Andean Giant. This machine faced unprecedented challenges due to the Andes' notorious seismic activity and the presence of tough silicified rock, which required custom-engineered cutter heads to break through. The tunnel now facilitates the transfer of 2 cubic meters of water per second, which is intended to irrigate 43,000 hectares of land, equivalent to the size of more than 60,000 football fields. Moreover, the Almos project has introduced an innovative water management system that includes not only the tunnel but also a vast network of canals and reservoirs designed to optimize water use across agricultural and energy sectors. The project's location in one of the most seismically active areas of the world required sophisticated geological surveys and adaptive construction techniques to mitigate potential earthquake damage. Despite this challenge, the completion of the Almos Tunnel has transformed a once parched region into one of Peru's most fertile agricultural zones. Next up, we have to move over to the United Kingdom for the Liverpool Street Station redevelopment project. This endeavor is focused on enhancing capacity, improving accessibility, and upgrading facilities to meet the demands of increasing passenger numbers. The station, originally opened in 1874, is undergoing a significant overhaul to integrate contemporary design elements while preserving its historical character. A key feature of the redevelopment is the expansion of the station's concourse, which will increase the available space for passengers and reduce congestion during peak times. This includes the construction of new entrances, wider platforms, and additional escalators and lifts to improve the flow of people throughout the station. Sustainability is at the heart of the Liverpool Street Station redevelopment. The project includes the installation of energy-efficient lighting, water-saving fixtures, and a new waste management system designed to reduce the station's environmental footprint. The construction phase, which began in 2020, is scheduled to be completed by 2025. The redevelopment involves a substantial investment, estimated at around $1.5 billion. One of the difficult challenges of this project is maintaining station operations while construction is underway. To minimize disruption, the project team has implemented a phased construction approach, allowing sections of the station to remain open and functional throughout the redevelopment process. Another critical aspect of the redevelopment is the integration of Liverpool Street Station with the Elizabeth Line. This integration will provide seamless connections to other parts of London and improve travel times for commuters. The new concourse will connect directly to the Elizabeth Line platforms, enhancing accessibility and making it easier for passengers to navigate between different transport services. Welcome to the Muskrat Falls Project, a colossal hydroelectric power station on the lower Churchill River in Labrador. Did you know that the Muskrat Falls project spans over 100 square kilometers? The project harnesses the power of water, generating up to 824 megawatts of electricity, enough to light up over 500,000 homes. Construction kicked off in 2013 and, amidst various challenges, wrapped up in late 2020. The scale of this endeavor is staggering, with a final cost soaring to approximately 12.7 billion Canadian dollars. Originally estimated at 7.4 billion, the financial scope ballooned due to unforeseen geological challenges and logistical complexities. The construction of the dam itself is a feat to behold. The main dam, made from over 2.2 million cubic meters of concrete, stretches across 32 meters in height and an impressive 432 meters in length. The project utilized innovative construction techniques, such as the extensive use of large-scale prefabricated modules to speed up the construction process and reduce the environmental impact. The harsh weather conditions of Labrador, with freezing temperatures and heavy snow, tested the mettle of every worker on site. Muskrat Falls also integrates cutting-edge technology with a series of 204-kilometer transmission lines, known as the Labrador Island Link, which connect the power generated from the falls to the population centers. This technological marvel includes software that allows the power flow to be adjusted in real time, optimizing energy distribution based on current demand and supply conditions. Muskrat Falls is connected to the island of Newfoundland by a subsea cable spanning nearly 30 kilometers across the seabed of the Strait of Belle Isle. This is one of the longest subsea electricity cables in the world, a little shorter than the length of Manhattan. But Japan is arguably even better at constructing underwater tunnels because they constructed the much longer Seikan Tunnel, stretching 54 kilometers with a staggering 23 kilometers lying under the seabed. It connects the islands of Honshu and Hokkaido, piercing through the Tsugaru Strait. Completed in 1988 after nearly 2 decades of construction, the tunnel resolves the overcoming of geographical isolation and enhances connectivity. With an overall cost of approximately $3.6 billion, the Seikan Tunnel's construction presented formidable hurdles, including dealing with the seismic volatility of the region. The tunnel now serves as a critical link for passengers and freight trains, being one of the few ways to access the island.